The tutorials with Kurt Smith. Kurt has a PhD in plasma physics, and he's also one of our HPC experts at Cython, and he will be introducing you to Python and HPC. So, welcome everybody.
Thank you, Jonathan. So welcome everyone, and glad you're here with us. Anyone who has just come in, please go to that URL on the board, www.nthot.com/public_content/ksmith, and you'll see 3 links there. The first link is the exercise material. You'll need to download that and unzip it, and that will be the material we'll be working through during the exercise portion. And then there are 2 versions of the slides, PowerPoint and PDF. So you need to get one of those 2 versions if you want to follow along with me. You can download that later on if you like, just to have those slides available for reference. So as you're here, so you've read the course description, and you've probably seen the requirements, the required package as part of the course. We're gonna, this course is kind of grabbing pieces of lots of different things. So we're gonna move pretty quickly, and we're not gonna dwell on any one thing terribly long. So if you weren't able to get one of those pieces installed, that's okay. It's not going, no one piece is essential for the entire part of this course. So you won't be missing out. You can always return to that later, look at the slides, and work through it on your own if you like. There's one optional, well, let's see, there's one optional piece, which is MPI for Pi. The reason that's optional is because it's a bear to install. You have to have MPI installed underneath, and they have to install MPI for Pi on top of that, and it's not a trivial process. So we're not going to do any exercises on MPI for Pi. We'll just be looking at examples of using MPI for Pi, and you can return to that in your own way. And then there's also, you may have seen a PyCloud installation. Well, so you have to sign up for it online at pycloud.com, and then you have to install some things on your computer. We'll be going through that. Here you can follow along if you like. We won't be any exercise material on PyCloud. So, I hope everyone's able to get the pieces installed that are interesting to you. And if not, you should still be able to follow along all right, and hopefully get stuff out of this course. So as I mentioned, this tutorial is pulling in pieces from a number of different sources. So we're going to be touching on a lot of different things here, and hopefully there's a narrative throughout it that you can make sense of it. We'll be starting at making Python in serial as fast as you can, and then turning our attention to how to parallelize our fast serial Python code. And so the things we'll be emphasizing about the course, the tutorial are 1, efficient Python, so just how do we make Python itself as efficient as possible, and 2, how do we parallelize that efficient Python code, okay? And efficiency has a few different meanings, right? There's efficiency of the runtime of the code, and there's efficiency of the developer developing the code. And often if you're here, you understand that Python can bring tremendous improvements to the efficiency of the developer's time, or exploring different algorithms, exploring different ways to approach a problem. So, but we still want the Python code to run as fast and as efficient as it can. So, while keeping in mind the precious resources of the developer's time. So, how do we optimize for the developer's time? Well, we start with good coding practices. We make sure that we're using the best practices we can, so that we're not wasting our time development in things that can be fixed, that can be caught way ahead of time, just because we're lazy or because we were programming in anger. You may have heard that term before. I've heard it, a number of people mention that, where you're so frustrated with the code base you're working on, you're just angry all the time when you're coding, and you don't care about the quality of your code. You just want to get it done, get it fixed, get it in there, and run it. Right. Well, as time goes on, that frustration is going to build up in bad code. So we want to try to stave that off as much as we can. Right. You may have heard this quotation from Brian Granahan. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? So extremely good advice. Keep your code simple. Keep your code one level simpler than you think you can understand when you're writing it, so that when you return to that code, you'll understand it when you're debugging it, or you have to modify it or improve it for some reason. So some of the principles you probably have heard of, and they're extremely good to keep in mind when you're making hundreds of little decisions as you're deciding on what approach to take, what algorithms to implement. Keep it simple. You don't want to do anything too complicated, and don't repeat yourself. Those two things are going to vastly improve your code if you go, refactor your code, look at things where you're repeating stuff unnecessarily, get them in one place so that you're not having the possibility of the same piece of information in multiple places. One can change and the other one doesn't stay the same. You want to avoid that as much as possible. You want to try to limit interdependencies of your code. You want to boost coupling. Each unit is well-defined and contained, and then those units couple loosely to each other. They only program to each other's interfaces. They don't assume certain things about the internals of another component. You want to give your variables, functions, and modules meaningful names. Try to avoid mathematics names, although sometimes if you're implementing a formula from a paper, it may make sense to put a big comment in the comments of that algorithm. This is where I'm getting this algorithm from. It's from this formula from this paper. And you may want to use those symbols from that paper so you can have one-to-one correspondence. In those cases, it makes sense to do that, but in general, you want to give very descriptive names to your variables. So the first tool we'll be looking at here is called Pyflakes. So there are several static analysis tools in Python. There are a few out there: Python, PyChecker, and Pyflakes. Pyflakes is the simplest tool. It's not as noisy or verbose as some of the other ones, so it's not as annoying when you don't agree with it. It's fast and simple. It detects syntax errors, missing imports, types on names, typos on names. And integrating Pyflakes into your editor is highly recommended, and it does significantly yield productivity gains. So I'm just going to show you what Pyflakes looks like integrated inside of Vim. That's the editor I tend to use. So if we open up a Python file here, so Pyflakes is running in the background when I've opened up this file. Okay? And if you look here, there's nothing special about this file here. It's just a few lines of code, and the contents here aren't entirely important. We're just looking at the Pyflakes thing itself. So if I start a line at the top, and I say imp from scipy import star, if I wait a little bit, you see that from line, that from word is now highlighted in red. And that's Pyflakes telling me that there's a problem. There's not, syntactically there's no problem, but semantically there's a problem. And if you look at the line down here at the bottom of the screen, it's giving me an error message. It says from scipy import star used, and Pyflakes is telling me unable to detect undefined names. So Pyflakes is looking at this saying, when you import everything from a package, I can't help you with what you just imported. I don't know where that's coming from, so you're on your own for that stuff. And so right there, it's giving you an indication that there's probably a better way to do this. So let's say we want to change that, we want to improve that, we want to say from scipy.sparse import CRS matrix. Okay. And now you see Pyflakes is trying to be helpful again. It highlighted it in red, and the error message is CRS matrix imported but unused. So I'm importing something, but I'm not using it anywhere. What's going on? Right? So let's say later on down here, I say def func x, and I say CRS matrix. I forget exactly the syntax, but we'll just give it something here so it doesn't die. So now you see I use CRS matrix, and that red highlighting went away because now Pyflakes analyzes this code and sees, okay, you're good. So there are a number of different things here that Pyflakes is giving us help as we're writing our code. We don't have to go through a compilation or try to run it, see if there's an error, and go back to our editor. It's all right there, and it gives us immediate feedback. So that's all I'm going to say on Pyflakes.
Can it check if you're expecting a list and you pass a dictionary or something?
So typing stuff like that is very difficult to check in Python. And it's going to do as best as it can, but it's not going to be able to do very much. So that's just a general Python problem.
Is there any way to take Pyflakes and just say sublime text, or is that?
I would not be surprised. It has integration. It can be run from the command line. You can just run it statically on a Python file. You can say Pyflakes make Py. So in this case, it didn't find any errors, so it just returned with nothing. But if you, let's just put in something here. Star. So now you see if I run it statically on the command line, it gives me that error that we saw integrated into our editor. So there's that version of it, and then it's integrated into Emacs. Then you wouldn't have to be surprised if your editor of choice has Pyflakes integrated. So the idea here, catch bugs before you go to the next step of your, before you run stuff, before you move on to the next step where often bugs can be more expensive. So when you're debugging code, bugs inevitably happen, and it's very helpful to just get in the mindset of debugging and get a debugging workflow. Your main first focus is just to isolate the problem. Find the smallest section of code that's causing things to fail. Okay? And there are a number of different ways to accomplish that. You probably just develop those techniques over time on your own. But some guidelines here. One, make it fail reliably. Find a test case that makes the code fail every single time. It's very helpful to have a separate piece of code that's testing the code that you're running and you're concerned about. And you can, then that's code that's just sitting there separately, and you can run it back and forth with as you're making changes to the code that you care about. Divide and conquer. Once you have a failing test case, isolate the failing code. You want to know which module, which function, and even which line of code is doing this specifically. You want to isolate a small reproducible failure and make that into a single test case, your test suite. You want to change one thing at a time, it's very important, and rerun the failing test case. Changing one thing at a time is essential. No matter how long it takes you, if you change 3 or 4 things, you don't know which change actually caused the thing to fix or fail in a different way. You just want to be very systematic about it. Take notes and be patient. It may take a while. Certainly, you want to use the debugger to understand what is going on. The debugger can be the built-in Python debugger, or it can be print statements. It can be anything you want, but just to get feedback from the code that you're running. So, who here has seen the Python debugger or used it? PDB. Okay, good. Some of you have, some of you haven't. So we'll just look at it really quickly. PDB is a Python debugger. It comes with Python, so you have it already if you have Python. If you, imagine if some of you go to the IPython talk later on today, they'll show you even better PDB interaction with Python. But we're just going to show you the basic usage here. So if I so here's just a file that's going to have some trivial code in here. There's a function, takes a single argument, and I'm going to say from PDB, import PDB.set trace. So that's the magic line you use if you're doing this kind of by hand. This is essentially manually setting a breakpoint in my code. When the interpreter is reading, going through our code and hits that line, it's going to import PDB, and it's going to set a trace, and then we're going to get into the interactive PDB session. And then we can say, our next line will be print x, return x, star x. All right. I'm going to say func 10. So now when I run this file, Python pdb test.py, you see instead of, we call the function with the argument 10, it now hit that line, import pdb, pdb.setTrace, and now you see here, I do L for list, and it tells us that the next line it's going to execute is the printx line, so immediately after the import pdb line. And we have a few things we can do. We can say args, for the arguments to the current function that we're in. You see it tells us that x equals 10. We can, as I showed you, the L command lists the code, and it gives us an arrow to show our current spot. And then we can step through our code by saying n for next. And you see right here that 10 was output, because we said print x was our next line. And now you see here it tells us the line that we're at, so the file name, the line we're at, line 6, and then the function that we're in, func. And then you get an arrow, and then the next line that we're going to execute, I'm going to return x times x. We say n again, and you see here, it's still at the return line, but it's telling us now that it's returning from this function, and it's returning the value 100. And you hit n again, and see, we're actually exiting the module now, and we're at that top scope where we call the function. Not sure what the exception actually there is, but we have at least the ability to step through our code line by line, see, think what's going on, inspect the variables as they're being modified and things like that. There are a lot of features in PDB. It's a fairly primitive interface, but it's very helpful. You can modify variables in place. You can change x in the middle of your code. You can run code and little snippets of code if you want. So I pointed out to you, and I encourage you to look it up if you want to learn about debugging Python PDB.
Is there any way to run a debugger without having to go and change your source code?
So like some editors have the ability to set a breakpoint in the editor, right? I don't know if I don't use any that do. So those of you who
in PDB, you type I think B space line number, and that inserts a breakpoint right there.
you type
B space and the line number.
B. Oh, right. I see what you mean. Yeah. So what you can do is you can run Python. Right, thank you. So if you want, you can say. So you can run a module, a Python module, using the PDB module to step through stuff, and that's the Python-m PDB line, and it will just put you immediately in PDB session. And then if you want, you can say B, and then 7.
Okay, that's useful.
Yeah, it's a set of breakpoint, things like that. So. Moving along. So Python, as you know, parts of it are compiled in C. You can wrap other languages with it as well. So you have compiled code that you're using with your Python code. And when Python calls a compiled function, as we'll see later, it's dropping into a different language, and PDB isn't available there. So if your bug is in that compiled code, you'll need to use a different debugger in order to access that. And we won't go into using GDB here, but I just pointed out to you that there's the GNU debugger for C, Fortran, other languages that GCC supports. And here's an example of a session using GDB. So you call GDB with a Python executable, and then you get a GDB session with a GDB prompt here, and then you tell it what Python module you want to run. And then you put any extra arguments beyond that. Run segfault.py line. You see GDB tells us that it's starting the program, it's running, and then here it gives us information about the error that occurred in the compiled code. Here it's telling us it's getting a 6.7 segmentation fault, and it gives us information about the line at which that occurred, the memory location at which the segfault occurred, things like that. You have many similar commands available to you. And as we saw in the PDB session, that'll end for next deceptive build, things like that. So GDB is basically a lower level, debugger to use on your compiled code. So we go from debugging tips. Go ahead.
So the GDB thing, does it work with Cython code as well?
Cython, yes, and actually, I don't have time to go into it today, but Cython has its own debugger, CDB, or CDB, something like that. And so we'll be going to Cython in a bit, but so Cython lets you kind of smudge the boundary between Python and a compiled code. And Cython has this nice debugger interface that allows you to drop into the compiled code when you're debugging in Python using their special debugger. So you can Google for Cython and debugger, and you'll see more information on that. So looking at code optimization, so just how we're concerned with making our serial Python code run as fast as it can. So the first thing, of course, is just to make it work. Have a good test case, have good data that you want to make sure is testing your algorithm, making sure it's working correctly. We're going to write the code in simple and legible ways so you can understand it easily. We'll make it as one level below what you can understand so that when you return to it, it's immediately obvious what's going on in that code. We want to make it work reliably. We want to write automated test cases. We want to make really sure that your algorithm is right, and that if you break it, the test will capture the breakage. You want feedback from your test to tell you what broke and why. Optimize the code by profiling simple use cases to find the bottlenecks and speeding up those bottlenecks, and find a better algorithm and helping you to find a better algorithm for implementation. You want to keep in mind that a trade-off should be found between profiling on a realistic example and the simplicity and speed of the execution of the code. If your profiling takes really long, you're not going to do it as much. It's not going to give you as much feedback as you'd like. So there's definitely a trade-off there. For efficient work, it is best to work profiling runs that last about 10 seconds or so. So the principle of no optimization without measuring is very important. Oftentimes, it's very surprising what bottlenecks are in your code. And if you measure, you're guaranteed to get more quantitative data about what indeed is taking the longest time to run. So there are a lot of tools in Python to help us profile stuff. And in IPython in particular, it's very, very easy to use. There's no excuse not to profile your code. There's a time-it module, and then there's also a magic command within IPython. And for those of you who have not seen IPython, if you go to the IPython session this afternoon, you'll learn all about magic commands. So, but they're very, very easy to use. I'm just going to show you a quick session here using them. So we're going to import Numpy as MP, and then we're going to create an array. So 1,000 element array A. I encourage you all to program along to try this out with me if you like, just to gain experience and get used to it. So to time code in IPython, you can use the time-it magic command. You say %time-it, and the % sign in the first spot in a command in IPython tells IPython this is something special. I'm going to do something special with this. And in this case, we're saying I want you to time this next expression or statement, whatever it may be. And we're going to say a squared. So we're using a NumPy broadcasting operation here. We run that, and time-it then gives us this feedback, tells us it ran this for 100,000 loops. So it just looped over this tiny little statement 100,000 times. And it's giving us the best of 3 of those 100,000 loop times, and we're getting 2.85 microseconds per loop. Now, let's say we want to try a different implementation of this. We can do A times A. Well, let's fundamentally the same runtime. We don't, it may not be statistically significant. So A squared and A times A basically doing the same, taking the same amount of runtime. Let's see, do times A to the 2.1. So it's not the same operation, but just to show you that we're raising now to a floating point value rather than, well, let's just do 2 point. So fundamentally, pretty much the same. 2.1. Oh, that's interesting. So here you see time at A to the floating point value, the float 2 takes basically the same amount of time as A times A or A squared. But A to the 2.1 takes, an order of magnitude longer. Well, almost 2 orders of magnitude longer. So very small changes in your exponent result in significantly longer runtimes for this micro benchmark. So you get feedback then on what's actually taking what kind of time when you're developing your function or your algorithm.
So how do you optimize it? Because it's a floating point issue. Because one is an integer, one is that correct?
So how to optimize this here?
Yeah.
So in this case, I would drop into compiler code. This is extremely important, and it's very important that this one line run as fast as possibly can. I would drop into Cython or compiler code because there's not much more you can do here to get it faster. But operations like this can tend to just fundamentally take a lot of time because you're now getting into just not simple basic arithmetic operations.
Excuse me. I would expect that since you have a Numpy array already, you're already going into compiled code. So I would expect any more improvements.
Yes, it's a great question. So for many operations, yes, you are. So for instance, the A times A is looping over the memory in C. You compile the code, and it's doing that operation using a ufunc, using the machinery inside of NumPy. We'll see this in more detail in a little bit. But the issue here is the implementation of operations in NumPy are often very general and capturing the general case rather than the specific case that you might have. So if you know some way that you have more information to be able to say, I know in my case, I don't need this general infrastructure. I need it to be sped up by using this more specific stuff, and then you can get speed ups over runtime. And we'll see in the example in the exercises comparisons between just pure Python, NumPy, and compiled Cython code and how they differ in their performance. Any more questions? Great questions. So let's say you are beyond just profiling single lines at a time. You have you want to get more profiling information about the entire program as it's running. You want to get feedback on what functions are taking the longest time and where they're coming from, things like that. Well, there's a feature in Python again that allows you to run an external module within that session and get timing information as that's being run. So here we have a very simple Python module. It's importing some things, NumPy, Scipy is importing linear algebra module, and from independent component analysis, it's importing some function we defined here. Here's a function tests, creating some data. We're getting singular value decomposition of that, just random array or matrix. And we're getting the principal components out of that, SVD decomposition. And then we're calling myfunc on those results. So just some bigger things that we're trying out here. Now, call that demo.py. We can run it from within Python, and we say %run, like again, one of those magic commands. and we give it a -t flag, and that's telling run to run it with timing information or profiling information. And then we give it the module we want to run. And here IPython gives us the CPU timings, the user time, system time, things like that. This is 14 seconds or so. So that's just raw timing information. We want to get more detailed, like profiling information on which functions are taking, what amount of time, how many times they're called, things like that. There's this very, very helpful profiling mode for run, where you can say run %run -p and your module name. And it'll take longer than it would have run otherwise without profiling, because it has to inspect and do things that it's, as you call each function. But it's giving you back all this very useful information. Tells us how many function calls, that's after this completes. Tells us how many total function calls, and how long the total application took. And then it's going to give us this list here with all these different columns. And it's telling us that it's ordering these columns by internal time. First column is the number of calls. Well, each line is a function. So, for instance, this line here, this function is called 54 times. And you see here that it's calling numpy.core.dot. So that's the dot function here. And it's here we're only calling it once from within our script, but internally it's being called 53 more times by whatever functions we're calling. So you get all this feedback on, well, even though I'm calling this function once in my code, actually the code I'm calling calls it, 100 times, 1,000 times, 1,000,000 times. So even if this function is really small and seems to be running really fast, well, if you're calling it 1,000,000 times, then it makes sense to pay attention to that function and make it as fast as you possibly can, because it's a hotspot in your code. So you immediately get feedback on where the hotspots are, where they live, the time they take, and these other columns here are giving you time information, time feedback on that function. And there are different ways to think about how long a function takes to run. You can think about it in terms of just the statements inside of that function itself, not what that function is calling. When it calls another function, you want to ignore that. Or you can think of it in terms of, I want to know from the start of this function to the end of this function, how long it takes, and including everything else that it's calling as well. So that's what these different columns are telling us. It's telling us the total time in that function, and it's also telling us the per call time in that function.
Can we profile something else than a file? For example, one function that is already defined in IPython?
Yeah, IPython. I've not done it in a while. I'm pretty sure there's a way. I tend to prefer to put things that I'm profiling at this level inside of a separate file, because it's often at the point where I've got the algorithm correct and I want to just make it faster. So I would need to play with it a bit to remember. In terms of the run command, though, it's running an externally defined module. So unless anyone knows offhand, I don't know the way to do it with a function defined inside of IPython right there. So, but again, it's mostly because I've not tried it myself. So we have this feedback from profiling our code as we're running it using run-p. Actually, yeah.
So the feature in IPython here just comes with IPython, or you need to install other things to have that available?
The run-p?
Yes.
That's with IPython, because it's using the C profiler that's built into Python automatically. Yes. So here we're going to just show you run-p, run.py. Take a while to run. And you see how we get that information back. After it ran, it gave us the total number of function calls and how much total time for everything to run, and then we have our order by internal time line here, and we get this nice output. And we can scroll through and see everything that was called in excruciating detail. It's not necessarily the best format for getting comprehensive information, but you can just look at the top there and see what things are taking the most time. So like the first 5 or 10 things are often the most relevant things to look at. If you want a nicer way to interact with this profile information, there's something called Run Snake Run. It's a project that basically takes the output from the profiling information that the run-p command uses, and it gives us a GUI that we can interact with to see what's taking the longest and how it relates to the code that's calling it, things like that. So, let me show you that. So, if you look here, the commands you would use, oops, move that, select it. There it is. So this command here is how you tell Python to run a module, and while you're running it, output profiling information. This is just from the command line, this is from within IPython. And this gives you a file that is this, it saves all that profiling information that's necessary to give you the output that you need for the list profiler that we saw before. And we're going to use this to give a GUI of that profiling information. So first you run your code under the profiler. And so here we're saying -m cprofile, that's the profiling module that's collecting all the profiling information. We say -o demo.prof, that's the output file that's saving all this profiling information. And then we give the demo.py file, that's the one we want to actually run. Now, once that's done, we have a file in our directory demo.prof. And then once you've installed run snake, it's a separate thing from Python. You can say run snake and then the demo.prof file, and that'll pull up a GUI for us. And fortunately, I'm having display issues because when I do run snake demo.prof runs, there we go, excellent. The demo effect in reverse. I was having problems before, and it works now. I don't think I can count on that very much. But anyway, so what we have now is all the same information that we saw before in that list view, but it's all in GUI form. Okay, so you immediately get feedback on, and this, okay, so what's going on here is, here's basically the list of function calls on our left here, and you can click on it and we'll sort by that column, whatever it is. So here we're sorting on the number of calls. Our calls, I can't quite recall what that's referring to, but you know, run some documentation. You have other columns here, so a lot of feedback you go into. Actually, it's a great question. So there's, I just found this the other day. There's a run snake mem command, which is separate, which does memory profiling for you. I've not used it myself, so I don't know much more than that, but just mention it to you if you want to look into it. If you look here then, you have this GUI. It's all these nested boxes. Okay? And a box within another box means that that's a sum representing the amount of time, the size of the box is the amount of time it took. And if it's inside another box, that means that outside box is calling that inside box. Okay, so each box represents a function or something that's being called. And so you can click on these different boxes, and then your view down here, you're getting feedback on that specific call inside of that, you know, in that scope. You can click on some of these outer boxes, they're highlighted, and you get that information. So it's a very nice, explorable way to look at the runtime of your code and how long each thing is taking. So obviously here, SVD the SVD call is taking the vast majority of time. And then you have these other calls over here, which are, you know, percentages of our SVD call. So,
excuse me. If the same function is called from two different locations, it'll appear twice as two separate boxes. Is that?
yeah, that's a great question. I've not looked into RunSnake enough to know exactly how it does that, but yeah, I need to look at it a little bit more to understand exactly how it is. But.
I think what you tell is true. I've used it a little bit and they put different
It's in
bugs.
different places. Okay.
But with the tabs under, you can search in that, yeah.
Oh, okay. Fantastic.
All right.
Okay, great. We're moving a little fast, but there's a lot that we want to get through here. So, yeah, these are just tools to help you in your profiling, debugging, and speeding up your serial Python code. So, let's say we have module, and everything we've seen so far has given us just function level information. So, how long does this function take? And is it, you know, are we including the time that it's calling other functions, or are we just including the time spent just in this one function? But we don't get line by line information that way. Now, there's this, what we can use is modify our code a little bit using this profile decorator. And for those of you who have not seen decorators before, they're you probably see them more frequently the more you look at Python. So I encourage you to read up on them and learn about them. They're, in this case, for our purposes here, you can think of it as just we're annotating this function to tell, basically to let our profiler know, I care about this function, I want you to profile it. So ignore everything else, only profile the ones I'm annotating with this @profile decorator. So that's all I'm going to say about decorators here because it takes too long to go into them in detail. But if we put this in our code, this @profile decorator, and we run this kernprof.py line profiler on it, and we give it a few flags, L-B. We get this output here, which is pretty nice. It's giving us the line number, the number of hits, the number of times we call that line, the time that line took. I believe that's in microseconds. That information is given in this section here that I cut out. The percentage of the time in each line, and then the actual line contents on the right. Which can be very, very helpful to just look at your code, see, line by line, what's taking the most amount of time. Obviously here, it's the SVD call. I'll leave it just at that. You have all the information here you need to use it. Usually you don't want to do line profiling on too many things at once, just because there's a ton of information to take in. Often you want to just turn it on for a function at a time and use line profiling like that. Nothing preventing you from doing, profiling a whole bunch of stuff, but all at once. But I find it's most helpful just line profile one function at a time.
So when you use that, do you have to import anything?
No.
For the decorator?
That's a great question. You don't. It's really strange. I find that strange as well. But what's going on here is it's just looking for this line, and it does some magic to take that function that's being decorated and make it work. I think I should show you the source we're using here. Right, so you see here I had it before. I had @profile, and Pyflakes is trying to be helpful and saying where the heck is this thing coming from, and I'm specifically not importing it from anywhere, and I can say kern prof-l-v demo.py runs, takes time, and we get that output. So see, we didn't have to say from current prof import profile. You just use @profile and it works. The line formatting is messed up a bit just because the screen size here, but it's the same information as the slide. We have the line contents, time, for things like that.
And what happens if you run it but not under current prof?
That'll be an error. So if so we get a name error there. So we have to go in and turn it on and off. So in some sense that's good because we're not going to be profiling when you're in production, or that's not gonna you're not gonna get hit there. So.
Do these profiles work well when you use the multiprocessing module? So for example,
Great question. So profiling in parallel is really hard. It can be a total pain because you don't have as much control over what's running when, where, what node, and things like that. So when you're profiling, it's strongly recommended that you profile in parallel, and you profile in serial. And
then how do you optimize parallelization? So for example, if you use a multiprocessing module, there's this parameter called chunk size. It's always hard to set the chunk size optimally anyway. So
you just have to go up to the next level of granularity. Like you have to be able to pass in your chunk size as an argument to the entire program, but you don't have to. I mean, this is one way to approach it. And then you can change your chunk size and see how the total runtime is changed by that. Or you can create a small test over here that's just testing that aspect of your parallel program, and be able to just isolate that part that you want to profile. But that's a very general, very difficult problem is profiling and optimizing parallel code, just because you don't have the determinism that you do with serial code.
So there is also a line-by-line memory profiler. I think someone wrote it that's floating around GitHub and that works with IPython. It'd be nice if there was both a CPU and memory profiler in one, so you can actually run them both one by one.
I agree.
Can you repeat the question?
Oh, the question is, there are some memory profilers floating around, and it'd be great to have, and specifically for Python, and it'd be great to have memory profilers that basically work for both the CPU and for
One module does both.
one module that does both, and specifically both Python and CPU memory profiling. And memory profiling in Python can be challenging, but it's a very important feedback to get, and it's not as robust often as time profiling. So doing okay in time, but we're going to be moving a little quickly through these next sections to get to the setup for the exercises here, for the exercise section. So this is just a slide emphasizing that you should be aware of and try alternatives. There are, unfortunately, multiple implementations of linear algebra routines in Numpy and in Scipy. And there are multiple implementations of FFTs in Numpy and in Scipy. And it's often that way because of legacy reasons. Numpy had it first, Scipy wanted a newer, shinier version, so it uses that, or there are specific performance issues with certain algorithms where you have this one over here and that one over there. But when you're using a specific module, specific algorithm, you'll learn often that, okay, there's a couple of different ways to approach this. Well, you want to make sure you try all those alternatives. Here we're just looking at the different SVD implementations, one in Numpy and one in Scipy. And you see that the Scipy version gives us the ability to turn off the full matrices that are returned. We don't have to get full matrices back, we just get the essential information back from these routines. Okay, so, and you see that the Numpy version doesn't have that capability. So it runs and it takes 14.5 seconds. We can run the Scipy version the same way, it runs essentially the same amount of time, but if we use the Scipy version with this extra feature, where it's not giving us back a lot of redundant data, then we get orders of magnitude speed up as a result. And this is just very specific knowledge you have to gain over time. It's not anything you can just necessarily learn without doing your homework and doing your background work and understanding the different ways different algorithms are implemented and where they live.
How do you specify the number of the rank of the return matrix?
I don't know. It's been a long time since I've used SVD, but we can talk about it later. So looping constructs. Often in Python, it's for those of you who have been doing numerical work using Python, you often know that for loops are to be avoided if you can. You want to get those loops to be implicit loops and in compiled code. Oftentimes you can't avoid it, so we'll go over some, later on we'll see how to do a for loop and how to optimize as much as you can in Python. But one way to take a for loop and convert it into something that's looping implicitly in C is to take your loop and convert it into using map. So here we have a simple loop that's looping over old list, and it's just appending the uppercase version of that word, of each word in old list to new list. Now, very easy to convert this to using map. Say, it's a little different syntax for those of you who may not have seen it. What map does is it takes some function, some callable, here the string.upper function, and we're applying it one by one to each element of old list. And the results of that are collected into a new list, and that's just returned from map. Who here has seen or used list comprehensions in Python? Okay, most people, great. So list comprehensions are kind of the Pythonic way to do the same sort of thing. They provide a syntactically more compact and more efficient way of writing the above for loop. It's pushing the looping into C code, essentially. It's still doing Python operations, but it's going to be a bit faster than looping over this word in old list explicitly here. And say s.upper for s in old list. The syntax is a bit easier to read as well. There are generator expressions. Who has seen or used generator expressions before? That's this thing down here. Okay, a few people. So the only difference between these two syntactically is that list comprehensions use square brackets. Generator expressions use parentheses. And semantically, though, the result of this is a generator. And what that is something that when you ask for it, it gives you back each thing that it's creating in that iterable, that list, one by one. Whereas this list comprehension does everything first, and then it does all the computation first, and then returns the results of that computation. So it's on-the-fly computation.
So I don't really fully understand why this comprehension is so much faster. I read someplace that it's being done in C. It doesn't really make sense to a certain extent.
Yeah, great question. So what's happening, think about it in terms of the interpreter. This Python is stepping through this code. Line by line, it's for this explicit for loop up here. It's hitting this line, and it's going to basically do all the setup for this loop. And then after that, it's going to hit the next line, the body of that loop. It's going to run that line, and it's going to run the next line, the next line, the next line, in sequence. And it's not going to be able to combine those operations or do anything more intelligent just because of the nature of Python. It has to go line by line, one by one. Once it's done with the body of this loop once, it goes back to the top, basically iterates through this list to the next element, sets word to that element, goes through, right? In the list comprehension, what's going on is it's able to, if you look inside of the compiled Python source code, you'll see basically a loop, with a while loop or for loop there, but it's using an internally, the actual loop itself is implemented in compiled language. It still has to do the same iteration through that Python object, so it's still doing Python calls. But the overhead of stepping through, setting that thing to the next element, things like that, it's going to be reduced by some small amount, but noticeable amount for the list comprehension. Part 2 is also able to use specific iterators for list comprehensions that it's not able to pull out for explicit for loops, and a few other things as well. So there's small differences, but the cumulative effect is often noticeable. The other effect too is that list comprehensions, they're often simpler. You're not able to do a general operation of list comprehension. So because of that, you can often have each list comprehension is going to run a little bit faster because you're not going to be pulling out all the same machinery as you would for a general looping statement. Go ahead.
I've always been a little bit vague how to use those, like how to use iterator in a generator expression. Do I use it like it's a list or something? Iterator zero, or what do I use it?
Great question. So here's a list of characters. So a list of single characters. Okay. So we're gonna say iterator equals, so upper for S and equal cars. So there's our generator expression, or iterator. You see what that thing is a generator object, genexpert. Okay. Now, what you do is later on, that lets you can iterate through that thing one by one, and it will just run that operation each time. It's not going to be pre-computing anything, it's just going to only be computing things as needed. And so we can say for upper CH in iterator, upper CH. So you see, so we iterate through it using a for loop, or we could use a list comprehension here or something else. Or you could say, we'll do iterator again. You could just say list iterator, and where the list constructor will implicitly loop through or iterate through whatever thing you pass in, and it's going to actually give us a list back with those contents in it. So it's basically something you create and you iterate through it later on in some way, some fashion, and it's only giving you things back as needed.
I think what helped me understand that is it calls the .next, I think.
Ah, right, yeah.
Under the hood, I mean, that's...
Thank you. Yeah, that's right. So if you look at the methods that are available on an iterator, there's a .next method, among other things. And under the hood, what's going on is whatever's iterating through this is just calling .next. We get A, here's B, here's C. We call it one more time, we get a stop iteration exception, and that's how that thing knows it's done looping through this generator. Thank you.
So is that in the order of preference? If you can use a map, use that. If not, use a...
It's more application dependent. Sometimes you know that you're going to need the thing anyway, so you're going to need it as soon as you iterate through it, so that you don't need to defer the iteration necessarily. So you just use a list comprehension rather than a generator. Sometimes you have an infinite stream, a stream that doesn't end. Let's say it's a stream from some data source that is really never going to end for your application. Well, in that case, you can't iterate through the whole thing. You'll never end, so you have to use a generator. Right? In other cases, it's pretty clear. You can understand it when you use map. It's not too complicated. So you prefer to use map rather than a general for loop or something like that. And you get a bit of a speed increase by using map. If you have to, if it's a really complicated looping construct, and you've got it as simple as you can, but the clearest way to express it is in a for loop that's not killing you in performance, then you just use an explicit for loop. So, a number of different approaches there. So, in Python, whenever you do a dot lookup, you say object dot name, Python, it hits Python's basically attribute lookup mechanism, and you can read all about it on python.org for documentation. It's a very complicated complicated sequence of steps that Python does every time you do a dot lookup on something, just to make sure it's capturing everything you possibly would want when you do a dot lookup. So, for instance, if you have a class, it's a subclass of a subclass, and you've got complicated inheritance and things like that. When you do a dot lookup, it could possibly be something that's inside of that object that doesn't exist in that subclass, but in a superclass. So it has to eventually work its way up the inheritance tree to find that thing. So this is just a long roundabout way of saying that dot lookups can actually be a performance bottleneck in type loops. So you want to try to avoid that if you can, in cases when it matters. So here we have a for loop, and it's the same for loop as we saw before, except the only difference is that we've now basically made aliases for these objects that we're calling inside of this for loop. So here we're making an upper alias, and it's the same thing as string.upper, but it's just creating a local variable upper that is string.upper. Again, we're doing new list.append, so it's the append method for the new list object, and that's the append variable here. And now in our for loop, we're saying append upper word. This is identical to new list.append with word.upper inside of the parentheses. So this is identical behavior. The only difference is that we're creating aliases, local aliases for these callables to try to get a bit of a speed up as a result. And this only makes a difference inside of type inner loops. When these things are run a lot, it's going to be, simplifying. It's going to be cutting off that lookup mechanism that Python is doing every time you do a dot lookup.
So what about if you do extend as opposed to append? So if you have a list and you're extending things, what would you do in that case?
In that case, you would do the same sort of thing. You would just say, here you can say extend equals new list.extend. And then
why is the function, so the string.upper is that a function pointer that you're pointing to? Why is it so much faster?
Just because whenever you do a dot lookup, whenever Python hits this line, new list.append, if this were, so actually this previous slide here.
Compiler take care of that for you, or the interpreter?
The Python interpreter is very, very simple. It doesn't do many optimizations at all. And it's partly because in some cases it can't, because you can redefine string, str. You can change that to be something else. So your str could be, you could redefine str, and then you can redefine str.append to be something else as well. So it's not going to know the shortcut to go to the compile and built-in string module. It could be some general thing. It's just, as far as the interpreter is concerned, it's just a general name. Okay. And actually, this is actually a good point because
so things like PyPy will take care of that.
Yes,
for you there, right?
That's correct. And Cython, we'll see in a bit too, has the ability to do that as well, to shortcut those sorts of things.
What's the version for the mix?
Definitely outside of the scope. But let me show you this though, because this is actually really useful if you want to get down to the next level to see what the interpreter is doing. So let's have a function here, and let's just put our new list. Nothing word in old list. Okay, so there's a function. I'm just using global stuff. Okay. The only reason we're putting it here is because this is what you have to do for this tool I'm going to show you here. I don't have any slides on this, but it's relevant to some of the questions we're being asked here. So there's a dis module, it's short for disassembler, and you can say dis.dis and give it a callable, so a func. And so what this gives us now is output. It's a Python bytecode that's being executed. And you can step through this, and it's primitive, the primitive operation. So I'm not going to go through all this, but you can drop down to that level and see exactly what's going on inside Python. So for instance, here it's setup loop. Okay, that's the for loop line. Here's loading global, all this. Here we're getting an iterator. Now it's doing the for iteration here, and it tells us where the end line is at. What that is going to be is 41. Okay, so all this from here to here, from 13 down to 41, is the body of the for loop. Okay, and then all this in here is the body of the for loop. What's going on?
What does the 25 mean?
Question again.
What does the 25 mean?
So the lines in front here?
No, on the for iter is 25 to 41.
Right. So the 25. I don't know all the contents of the disassembly output. Sorry, but I know the 241 is telling you the bytecode instruction that it's stopping at. Okay. And some of this is information that's added to this by the disassembler module, and some of it is just the bytecodes themselves. So I just refer you to this documentation to get the comprehensive stuff. Sorry, I don't know more about this, but if you ever want to know what's going on, this is going to be very instructive to see what Python's doing. And one thing I should point out though that's relevant. You see here you have these load globals and load fast. Okay? And load fast is indeed faster than a load global. Load fast is doing a local lookup inside of the scope of that function. It's going to be faster than a load global because it has to do a search inside of all these different namespaces all over the place. Okay? That's all I'm going to spend on the dis module, but it's there if you want to go and see what bytecode the interpreter is executing. So if you were to, leave this as an exercise if you want, let's say you were to re-implement this function that I just showed you here in terms of these alias functions, you would see that a lot of these load globals that are in here have been converted to load fast. Okay. And that's essentially what's going on underneath the covers. It's doing a local lookup rather than a global lookup for these different things. So here, he's leading on to the next slide. Right? So, local variables are faster than global variables in Python, significantly faster, and especially for tight inner loops. Okay? And so, what that means is when you're inside of a function and you know that function is being called a lot, and that function has a loop, a for loop, or like a nested for loop, even more relevant. Nested for loops. Oftentimes what we want to do to get a little speed up is to intern your variables, to make all the loop variables local. And you do that by just creating a variable inside of your function body that refers to the things that you're using inside of your loop body. So that's what we did here. So your loop body is append upper word, and append and upper are the things that we saw in the previous slide, right? They're the local variables that are just referring to those callables.
Could you define local a little bit more? Here it means within the defined function.
Right.
How local is within the module? And
that's a great question. So there are a number of different namespaces in Python. The local namespace is whatever your context you're in right now. So if you're inside of a function body, the local namespace is a function scope. If you're inside of a class definition, there's a class scope essentially. And then if you're inside of a method inside of a class, you're inside of that method's scope, inside of that class's scope. And then there's a module scope outside of that, which is everything basically at the the left boundary of your nothing indented essentially. That's your module scope. And then outside of that, outside of everything, is the built-in scope. And that's where all the kind of default built-in stuff lives. So like your list constructor, your dict constructor, your set constructor, all this stuff that you just use without having to import anything from Python. That's the built-in scope. And Python, when it tries to find a name, when it's doing that load fast or load global, actually I should say, load fast knows that it's in the local scope, so it can just go right to that thing right away. Doesn't have to do any other, doesn't have to look anywhere else to find that thing. When it's doing a load global, what it's doing is it's first looking at your local scope, then looking at the next outer scope, then the next outer scope, et cetera, all the way up to the built-in scope at the top level. And each one of those, it's trying to find whatever that thing it's looking for. And there's some other aspects to it that I'm not going into here.
So what you're saying is if I define like a bunch of tools in one module, and I've got the main body in another module, that what I should be doing is redefining the functions in those tools.
Not redefining necessarily, but creating an alias.
Creating an alias.
Right. If it matters. Like, this doesn't matter in almost all your code. It only matters when you have a loop that you know is taking a lot of runtime, and you get a little bit of a boost by doing this. I mean, it's going to be 10% at most, I would think. But if that matters, it's a really tight loop, then that's relevant, right? For the rest of your code, I wouldn't worry about this until you know this is a tight loop that matters, right? Using all the profiling tools we've seen. So, and you're basically converting the load globals into load fasts. Is what's going on at the interpreter level. Other questions?
Is because you put that in this function, you're creating a local namespace inside this function. So your point is to create functions around type for loops to create a local namespace?
Yes, absolutely. Yeah, exactly. You want this for loop to be looking up things in the local namespace. Is the relevant point. Yes, so you want to make sure it's all in that local name. If it's not already in a function, put it in a function.
That's right.
So in a sense, what you're trying to do is make it local to some stack or other. Is that right?
Yeah, that's right.
Any sense of how big that stack is? Does it vary by?
Well, the first sense is just how big your function is, essentially. Right? Do you mean in terms of how big in what sense exactly?
Yeah, how quickly can you just get off the stack whether you like it or not?
So that's a really good question. So,
Stack. That's what I mean. You're trying to contain the thing and keep it as local as possible, right?
Right. So, if I don't understand the question correctly, ask me at the break. So in Python, there are stacks, and switching, popping and loading a new stack is inherently somewhat expensive operation in Python. And so when you're in a stack, you want to kind of keep, and it's a tight loop again, you want to bring things into that stack and keep things there that are relevant to your computation. All right. Any other questions? Very good questions.
So if you just took the code, you pasted it into the global, if you took it out of the function, you just paste it in the global space, it would run slower because it has to do all the module lookups?
Yes, it would. Those load fast would be all local globals. And that's an inherently slower operation. Okay, so now we're going to be getting into more numeric specific optimizations. And again, we're just thinking in serial right now. We're not thinking in parallel yet. So this is the kind of outline. Those who went to the Numpy and Scipy tutorial yesterday? Okay, so you all have probably seen this before, and the rest of you, I imagine, are familiar with it. They've seen the tutorial level stuff, so we won't be belaboring Scipy and Numpy too much, but we want to at least go into some of the relevant points on the specific Numpy features that are relevant for optimizing your operations as much as you can without compiling the code. So as you know, NumPy should all be very familiar to all of you, so don't spend much time on this at all. So you have these nice operations on NumPy arrays that allow you to iterate over specific axes. You can, you all know about ufuncs, which allow you to combine arrays and expressions without having to explicitly loop over anything at all. And you also have these array calculation methods, which allow you to basically reduce your information down. So you have an array, you want to sum everything into just get a single value, which is the total sum of this array. Well, you don't have to loop over your array. You can just use this sum intrinsic defaults that have all the values in an array. You can specify specific axis to sum over, so you're collapsing along that specific axis. So here we have a 2 by 3 array. The 0th dimension has extent 2. The 1st dimension has dimension 3. And if we say sum A axis 0, we're summing over the 0th dimension. So we're going to add 1 and 4, 2 and 5, 3 and 6. The result is going to be a 3-element array. Should all be familiar to everyone, or at least makes sense given what you've seen of NumPy so far. Sum, if you say axis equals -1, you're going to be summing over the last axis. Okay? If you just say a.sum without any axis specification, this is the method version of the sum operation. You're just going to get everything summed together, so it's going to collapse everything down just a single value. And so, just showing you that these fundamental operations can be done without for loops. Okay?
I often have the problem where I've got missing data within an array.
Yeah.
And I've shied away from masked arrays for some reason. I want to know how much of a price I'm paying. If I've got missing data in there, then I end up having to do a for loop going through each row to filter out the missing data for that row. So how much is that really hurting me compared to doing a mask?
Fantastic question. So the question is how to deal with missing data and what approaches to take to deal with that, and then what sort of performance hit do you have when you have to loop through things explicitly. So there's actually a project out there. It's separate from NumPy, but it's called Bottleneck, and it has basically versions of these operations that handle missing data, that is designed to be as little slowdown as possible, but still be general enough to handle missing data. So I refer you to that because that's relevant. And then there is work within NumPy to incorporate in missing data NA arrays into the core of NumPy, make it have good performance. And you mentioned masks as well, and you said you say why you shy away from masks or masked arrays?
Well, it's probably not a rational reason, but,
okay.
But,
not for performance reasons, or just more for...
I needed the flexibility, and I didn't trust everything the mask was doing. So I ended up, defining my own missing, data character and working around it.
I see.
But I'm wondering if in the masked array, is it having to do an explicit for loop when it's going through, or?
Well, it's doing a for loop in compiled code, so it's going to be faster than if you did a Python for loop. So it's still going to give you the speed increase that way. It is having to combine more information to get the result out, so it's going to be slower. But it's not going to be as slow as if you did it in an explicit Python for loop. It's going to be a lot slower than a masked array version. Actually, so the exercise you'll see uses masked arrays, and so you'll get some experience with it. Hopefully, you can get more experience with it to see how to use that sort of thing for operations. Because masking in NumPy is basically how you do conditionals inside of NumPy arrays without having to pull out a for loop and have an if block inside of that for loop and break things down that way. So masked arrays are used a lot in the cases when you have to handle data, in different branches. So hopefully that got to some of your question there. Okay. So who here has seen this slide before or is familiar with it? Okay, some of you have, great. So I won't talk about it too much, but this is just showing you the internal ND array data structure that's inside of NumPy. So this is a C data structure that is kind of the core of what the NumPy array is. So inside of here we have some continuous block of memory. It's allocated in C, or possibly in Fortran or some other language, but some continuous block of memory. And that's the data pointer. And it's there's all this other information here, strides, dimensions, dim count, and D type, which is metadata on top of this kind of just contiguous blob of memory.
Does dimensions shape, right? Or is it a different thing?
Yeah, dimensions essentially is shape, that's right. And if you were to take this data structure and, just ask Python, what does this look like, this NumPy array look like, you would get this as a result, 0, 1, 2, 3, 4, 5, 6, 7, 8, and a 3 by 3 array. So all this information here is equivalent to this ND array when it's output. And you see here that we have these, first thing you have is a D type, which is a pointer to some NumPy D type object. And in this case, it's a float 32 D type. Dim count is 2, so it's a two-dimensional array. And then you have your dimensions and strides. So dimensions is 3 by 3. First dimension, number of rows is 3, number of columns is 3. And the strides here is maybe not incredibly obvious, but it's very, very useful. Strides is telling us how many bytes to skip over in that specific dimension to increment that dimension counter. Okay, so if you look at this here, strides is telling us you skip over 12 bytes in the rows to get to the next row, and you skip over 4 bytes in the columns to get to the next column. So who can tell me if this array here is laid out in row major or column major order? You should be able to look at the strides information and tell me that.
It's row major, right?
Row major or column major? So, okay, so let's change the terminology. Is it laid out in C contiguous order or Fortran contiguous order? What was it doing? C contiguous order, right? Okay. And that means that you increment if you want to iterate through this array in memory layout order, which index do you vary fast? The row index or the column index? Column index, right. So, that's right, and that information is provided in strides. And one really nice thing about this is if you want to switch from, for example, if you want to do a transpose of this array, what NumPy does when you do array.transpose array.t is it doesn't change the memory at all. This data is completely untouched. All that happens is it has to update this stuff here. D type's going to stay the same, dim count's going to be the same. It's going to change around dimensions and strides so that it now is going to be iterating through this thing in now transpose order rather than the original order. So, and that's just one example. NumPy can do all sorts of stuff without having to actually touch the actual data and move it around in memory. And it tries to do that as much as possible for you without having to create extra copies of data or touch a lot of data that it doesn't necessarily need to. So all this metadata is very, very useful.
Sorry, so when you're NumPy arrays are single strings, that's how we know the answer to the question. But when you iterate through it directly as a matrix, you're just going straight down the list. When you take the transpose, right, and you're now going column-wise, you have to jump each time.
You do have to jump, that's right.
Is it much slower than?
It is, but for certain applications, it may not matter. It may be that your bottleneck is touching all that data rather than iterating through it for whatever reason.
You always have the option of doing .t.copy.
Exactly, that's right. You can create a new copy of that array, and that copy will be contiguous. Then you have to, then you do memory map the arrays or something like that. So it's on disk rather than in memory. So, but yeah, it can be a challenge. So NumPy views, because you have used NumPy, you've been using views, if you haven't even known it. Whenever you take a slice of an array, you get a view back. All that's going on is it's updating this metadata and it never touches the underlying allocated data at all. So we'll see that here in this next slide. Here we have our big array A. So it's this, you know, the stuff in white in the background. And when we take slices of this array, kind of it's color coded, so we're just picking out chunks of this array, regular chunks, without copying anything at all. So whenever you're taking slices of an array, you're not making copies. And again, slices, for those of you who may have just seen it yesterday, slices are when you're using this, you're indexing into something, like a NumPy array, and you're using these colon separated indices to specify the lower, upper, and step bounds or something. So here, this yellow, orangey color here, I'm colorblind, so if I get the colors wrong, please excuse me. But that's this 3 and 4 aligned here. Okay, so we're taking the 0th row, and then we have a slice in the columns. So we're starting the 3rd value and going up to, but not including the 5th value. So, and again, everything in NumPy is indexed from starting at 0. So we're going to take the 0th row, and then we count 0, 1, 2, 3, start there, up to the 5th, but not including the 5th. So that's why we get this little block here. A 4 colon, comma 4 colon. We're starting at the 4th row, so that's here. And we're taking the 4th row, every row after that. And then we're starting at the 4th column, and every column after that. So that's that little subblock down here. Now this red stuff here, we're taking every row. That's what just the bare column means. Starting implicitly means 0 to n. So every row, and the second column. So that's just what this is here. So that's how you grab a column out of the NumPy array. If you want to put strides in there to skip over stuff, and that's very easy to do. That you put that in the 3rd slot of your slicing index, and that's how you get this kind of non-contiguous block of stuff. Every single one of these operations is giving you back a NumPy view, which does not create a copy. It's the really important thing to remember about views. Whenever you use just bare slices in a NumPy array, you do not make a copy. It's unlike MATLAB in that regard. And this is extremely useful. You can, if you have an algorithm that's shifting arrays back and forth, and combine stuff with kind of shifted versions of the array to kind of do like a finite differencing or smoothing operation, you can create a whole bunch of views that are shifted views of this array, and they don't make a copy. And then you combine them in some operation, and then that operation ends up making your end up. That's where the copy occurs, but the views themselves aren't copies of your original array. There's fancy indexing, which does make a copy. So we saw just regular slicing indexing, which does not make a copy, that makes views. Fancy indexing does make a view, a copy, excuse me. And you know something's fancy indexing when you don't index into an array with the simple slicing syntax here, the colon separated indices. Here we're indexing into an array with 2 tuples, okay? And you see here the tuples are the same length. There are 5 elements in each tuple. And the result of this fancy indexing is going to be, you just kind of go down the list of things you're indexing into. You have 0 to 1 element, the 1, 2 element, the 2, 3 element, 3, 4 element, 4, 5 element. So you're going to get this diagonal section of the array. And that's going to return a copy of that. Here we're slicing in the first dimension, but we're indexing with a list in the second dimension. So that's fancy indexing, so it's going to give us a copy. Here's a mask. So those of you who have used NumPy much, you've probably seen masks before. You'll see it in the exercise for those who care to work in that section. And masks are basically just Boolean values, zeros and ones essentially. And when you index an array with a mask, it's going to select the stuff that's true and ignore the stuff that's false and give you back a copy. So here our mask is selecting out these elements, 2, 22, and 52, and it's ignoring everything else. And we get this copy back as a result.
So is fancy indexing anytime you put in a tuple or a list? That's by default fancy indexing and copies, or?
Yes, that's correct. Sure. And so if you can express things, so slicing is very regular. Start and optional step, regular step, right? And so since it's very regular, very compact way of specifying something, NumPy can just update the metadata.
So NumPy knows that by default, it looks at the argument says, oh, this is there's a colon in here, so therefore we're not going to copy.
Yeah, what happens is that colon is converted into a slice object and with slice up. So when you index with a slice object, it just gives you a view back.
What about getting the diagonal of a matrix?
So there's an intrinsic function called diag.
Do you know, does that do a copy or does that
It'll give you a
view?
It'll give you a copy, yeah. Unfortunately, it can't give you a view because there's no way to express that just using a simple slice into an array.
I mean, if it's continuous, you might be able to work with the strides to find a view of it, right?
I'd have to work pretty hard to see if it could. I don't know if it could, but if you can, let me know.
So I mean, if you lay out the rows all in a row and you just do a stride of n+1, then you'll end up with the diagonal. But
you will, but it's still not regular. It's not going to be. You can't express it as start, stop, step, because the step is increasing each time, right?
No, it's n+1 each time because you're just going the n to get to the next number.
I see what you mean.
So does NumPy do that internally, or?
Good question.
Yes.
It does. Okay.
Then I've just done a fix for the case where you can take the diagonal of more than 2 dimensions.
Okay.
All right, we're gonna keep moving here to definitely get to the section. Just get up to the exercises before the break. So with array broadcasting, then, who has seen or heard of array broadcasting before? Okay. So array broadcasting is what goes on when you combine arrays in ufuncs and the arrays don't have the same number of dimensions, or they don't have matching shapes. Okay. The shape of an array is the number of elements in each dimension. So if you have a 3 by 3 array, the shape is 3, 3. Or if you have a 10 by 20 by 30 array, the shape is 10, 20, 30. So it's just that list of extents in each dimension. Okay. Well, NumPy has this really nice feature of allowing you to combine arrays using ufuncs. So a plus b is a ufunc, is the add ufunc. A times b is the multiplication ufunc. When you combine arrays using ufuncs, and they don't have the same shape or the same number of dimensions, NumPy applies a broadcasting rule for you. And you can use these to incredible benefit. This is one of the most powerful features of NumPy, and it's a shame it's not used or known about more than it is, because it's extremely useful. So again, so you have different dimensionality and different shaped arrays, and you want to combine them in some expression. There are 2 rules that are encapsulated in the term broadcasting. Okay. The first rule is if you have a 3-dimensional array and a 1-dimensional array, the smaller array, in terms of dimension, is going to have 1s prepended to its dimension until it matches the number of dimensions in the largest array. Okay. So I don't have a good slide on this really, but well, actually the next slide isn't too bad. In NumPy you can add a 1 to an array shape any place you want. It's going to change the dimensionality, but it's not going to change the underlying data. just prove it can. So here's A, it's just 10 zeros, one-dimensional array. You can say A-shape. You see it's just, there's one slot in that tuple, it's just it's just, one-dimensional array with 10 elements in that dimension. Now I can say, I can change A's shape. I can say A-shape equals 1, 10. Python doesn't complain at all, it's perfectly valid. And now when you see what A looks like, it looks pretty much the same, except you notice there's an extra set of brackets there. Right? And that's that extra dimension that I just added to that array. I can change A shape again if I want. 1 by 10 by 1. And you see now it's this crazy shape where it's got 10 elements in the second dimension and 1 element in each, the beginning and last dimension. You can do this all day long. You can add ones in any slot you want. Okay? It's not changing the underlying data, it's just changing the dimensions and the strides and things like that, the metadata around that NumPy array. And so when you're combining arrays in an expression and one array doesn't have the same number of dimensions as everything else, you add ones to the beginning. Then the second rule is dimensions of size 1 are logically repeated without copying, and then combined with the larger arrays.
I have a question.
Can you repeat that again? Go ahead.
Can you go back to the calculation you?
To the example?
Yeah. So can you multiply the row and column to make a square matrix?
I'm not sure. Oh, I see. So see me at the break. We can talk about that in more detail. But yeah,
if you want to calculate more, for example, if you want to do some eigenvalue analysis, you need to have a square matrix.
Right. Yeah, we'll just see an example of that coming up. So you'll see that in a little bit. But that specifically, you'll see how to make a square array using one dimension. So rule 1, prepend once the smaller array shape. Rule 2, dimensions of size 1 are repeated without copying, and then combined with the larger arrays. Okay, so it's easier just to kind of show what's going on rather than to try to explain it in gross detail. So here's an example. We have a 4x3 array and a 4x3 array, and we combine them, so they're the exact same shape, so there's no problem there at all. There's no broadcasting going on here. Okay. And if you notice here, the 4x3 array has, everything's the same in the rows, and the second array is everything's the same in the columns. So you can more compactly represent this operation using broadcasting. Here we're combining a 4x3 array with a one-dimensional 3-element array. And what happens is ones are prepended to this array, so now it's a 1x3 array. And then that 1 is basically logically reproduced without copying 4 times to be able to allow you to combine that with the 4x3 array. So think of it as you're stretching that 1x3 array in rows to match the larger array. Now here, we're combining a 4x1 array with a 3-element array. 4x1 array is reproduced 3 times in the columns. Yeah, so the 1 slot, the column slot. The 3-element array has a 1 prepended and then is logically reproduced in rows. So now you are combining a 4x3 array with a 4x3 array, and it works. But the important thing here is no copying is being done. There's no reproduction of data unnecessarily. So all this is being done in a memory efficient way. So here's A, it's array, column array 0, 10, 20, 30. B is this simple array 0, 1, 2, it's row array. And here we're combining A and B by telling where to put the new axis. Okay. we're basically saying append to 1, so there's a 4x1 array, and then combine that with B using the broadcasting operation. So that's the result of this operation here. So
But you wouldn't actually get those numbers in that third one, right?
Yeah, you would. Or,
So you're doing an actual addition of the 1 plus 10 and stuff like that?
yeah, absolutely. Yep. Yep. So if you put this into NumPy, these lines here, not enough time right now to do it, but you would get this 4x3 array as a result. Okay. So here's an application. Get the distance from the center of an array. And here we're creating 2 arrays, A and B. A is just a lin space, so for those of you who've seen MATLAB before, you've seen lin space before. We're creating a column array out of A, so it's now a 15 by 1 element array. We're doing A squared plus B squared and adding them together, and this is where the broadcasting takes place. Okay. And then we take the square root of that result. So A and B are, 15 by 1 array and then a 15 element array. They're combined, broadcasted. You get a 2-dimensional array out of this thing, just exactly analogous to this operation here. And now you get this distance array as a result.
What is new access in the A definition?
Good question. So new access allows you to basically place a 1 in any specific spot. If you remember, ones are going to be reproduced in that dimension. Okay. So if we do A colon comma new access, that is taking our 4-element array, and now it's making it into a 4 by 1 element array. Okay, so it's 4 rows with 1 column in each row.
So that's something understood by the bracket syntax? Or?
Yeah, exactly. Right.
It's in the NumPy namespace.
Yeah,
so if you have to import NumPy.
Oh, I do.
Yeah, thanks, Will. That's right. New access is an object that lives within NumPy. So you say from NumPy import new access, or say NumPy dot new access.
Thank you.
So I am going to blow over this slide just because it's going into some more broadcasting stuff. I don't want to spend too much time on it before getting to the exercise. So just a quick slide here on some speed issues with using NumPy operations. We can factorize for loops. Go ahead.
I just you asked that question about new access. Apparently, you can use none for new access as well.
None is actually, new access is none. That's right. It's clearer in your code if you use new access so people know what you're using. You're right. You can use none. Yep. So here's just saying you use masks and indices. Index arrays can be useful for to allow you to not explicitly loop over a NumPy array, but use it implicitly using masks. Broadcasting, which you just covered, you can use that for speeding up NumPy operations. And then there are in-place operations in NumPy that you can also use for speed up. So here, for example, we're seeing we're doing 2 different ways of calculating 0 times A. Not a very useful operation, but just for example purposes. So here it's 111 milliseconds per loop if you do A equals 0 times A. Here it's 48.4, so about less than half the time. If you do an in-place version of the same thing. So just talking about using views and not copies, which we already covered. So slicing gives you views, fancy indexing gives you copies. And here it's just talking about transposing and fortran ordering C order. It can make a big difference for certain operations. Here we're creating 2 arrays, A and B. We're taking the dot product of B and A's transpose. And if you do A.T, all it's doing is updating the metadata. It's not changing any of the underlying data. And you see that takes 194 milliseconds per loop. Now here we're creating a new array, C, from A's transpose, and it's creating a contiguous array out of that using NumPy.asContiguousArray. And now this operation is, more than twice as fast as a result. So the relevant issue here, though, is that the contiguous array operation can take a long time. So if it all depends on what your algorithm is. If you're doing this a lot, then you want to make a contiguous array once and just, gain the speed benefit. If you're only doing this once, then it doesn't make much difference. So, all right. So now, when all else fails, and you squeeze the last bit of performance out of your serial code that you can, and you still have to get it faster, then you drop into compiled code. So now we'll be very quickly and speedily going through how to some of the stuff you would use for speeding up Python code with compiled languages.
Maybe one last option is to use other Python library that optimize some type of computation, for example, numeric expression or Triano.
Thank you. Yes. So there are other tools out there that allow you to, and we'll actually cover one of those called memes. But yeah, there are tools out there that allow you to kind of get in between. You don't have to compile anything, but you get the benefit of compiled to some extent. You get the benefit of compiled code without having to compile stuff. We'll see that in a bit. Yeah, thank you. Good point. So these slides here, I'm not going to spend much time on it at all, but this is just showing you the nuts and bolts, the down and dirty C code that's underneath, kind of the framework that's underneath all Python extension modules. And here we have a C function fact, and it's inside, this is the header file fact.h, here's the implementation, fact.c. Here's a wrapper function in Python. Okay, it's written in C code, it wraps around this C function fact, and this allows us to call this fact function from Python. Okay. And the general pattern of, here you're calling this, you want to call this C function, underlying C function from Python. Well, you pass in your Python arguments. They're unpacked into C data types, passed on to your underlying C function. The results of that are wrapped up back into Python objects and returned. Okay? That's all that's going on here. And that's what this wrapper function is doing. Okay? And you see that's what's outlined in these comments here. These two lines here are just unpacking our arguments. We're calling our underlying C function. The result is then built up into a integer and returned as a result. So here's an entire Python extension module written in C. One slide that's only wrapping one single function, but everything in here allows you to basically call this fact function. So this is just to show you all the nuts and bolts of what's going on with all the benefit that Cython and these other wrapping tools are giving us.
Do your timing functions work with the Cython tool too? So you call it, does it take that?
So there is a profiling directive in Cython. You can say Cython, I think it's profiling equals true, or in a comment in the Cython source file. And Cython will let profiling give information about compiled code. So just Google Cython and profiling, and you'll find information on it. So all this is doing, here's our wrapper function in C. Here is the method table. So it exposes that wrapper function to the Python module. And here's our init function, which just initializes everything in a module. Okay. So very, very high level, these are the main components of our extension module. But you can see there's a lot going on here. There's a lot you have to know. There's a lot of dark corners here with memory management that isn't even exposed in this example. And we prefer not to have to program, if we want speed in Python in a compiled language, we prefer not to have to program using these, at this level. And so in the slides, there is a section on F2Pod, which I'm skipping over here, just for just a time. So that if you want, you can just code straight in C and speed up your program that way. But we're going to see a better way. Okay. Now, you mentioned Theano and non-expert. We're going to cover Weave here, which is a similar way of speeding up Python code. Weave is a way of basically taking an expression using NumPy arrays and handing it off to this entire infrastructure that knows how to parse that expression and stick it into a C++ file, compile that, run it, and give you back the result as if you had run it just in NumPy out of your interpreter. It's a really, really nice, handy little tool. It's particularly useful for just profiling stuff, well, not profiling, but speeding up things interactively, research-oriented code, stuff like that. It's not the sort of thing you would use in something you would deliver to a client, but it's something that you might use just if you're playing around and you need to speed up your code internally. So here's a case study using Weave. This will show you also how to use it in a little bit, what it looks like in use. We're using a very simple iterative solver for Laplace's equation. Here's our domain. We have 1 volt on the upper boundary, 0 volts everywhere else. We just want to see what the potential is everywhere inside of this domain. You can do that using this iterative expression here. And here we're using explicit for loops through NumPy array. So this is an extremely slow way of doing this. You can speed this up using NumPy expressions, but we're going to speed it up using Weave as well. I'm not going to go into details of this algorithm here in just the time. This is just to show you that but just keep in mind that this first version here is a pure Python. We're not using any NumPy specific features. We're looping through it explicitly in Python. Here we're using NumPy array expressions to do the same computation. You notice here the timing is 133 seconds for this computation in pure Python. Here we're down to 1.36 seconds, so 2 orders of magnitude speed up. Here we're using weave.blitz. So if you notice here, we have, we're creating a copy of our original array. We're doing the update, the core computation, and then we're calculating the error. You notice the core computation here is the exact same line here in Weave. We're putting it into a string, so we have triple-coded strings around it, and then we just hand that string off, this expert string, we hand that off to weave.blitz. And weave.blitz knows to look inside this string, parse it, find the different arrays that we're using inside of this thing, and grab those from the enclosing namespace, put it in compiled code, and run it, okay? It's doing a lot for us. And we get a speed up as a result. So we went from 1.36 seconds down to a little over half a second. There's weave.inline, which gives us a bit more control. We can be a bit more verbose. And here we have a nested for loop in C++. Okay, we're sticking that into our string. There's a lot more going on here. Again, of course, I don't have time to go into the details, but what we're using now is weave.inline, which allows us to have this greater level of control. And now we get down, another factor of 2 speed up. Okay. So with Weave, you're programming in strings. So you're putting code into strings, handing those strings off to the Weave infrastructure, and it then compiles, sticks those strings into the C++ modules, compiles it for you, and runs it. Okay. So because you're kind of putting your code into these strings, it can be a bit strange to be programming that way, but if you have a chunk of code you want to speed up, and you don't want to have to think about putting it in a separate file, to worry about, pulling out a compiler and doing all these things manually, Weave is a nice option. And I'm sorry I don't have more time to go into it. I'd love to go through an example with it. Go ahead.
So every time you do this, it gets recompiled in the background?
No, that's a great question. Thank you for bringing that up. What happens is Weave, every time you call this, the first time it's called, this compiled module doesn't exist. So it has to compile it then and call it. then the next time you call it, the next time this line is hit, what Weave does is it basically creates a hash of this string, looks and sees if it's already compiled the string with the same hash. If it does, it uses that. So it does a shortcut, never does a compilation again. If you change this string though, it won't find that version anymore and it'll recompile and do that. So you only hit the compilation overhead the first time you use it. Great question, thank you.
So what's the, because I see the NumPy array now has parentheses inside the C++ code.
So that's a great question. So so Weave.blitz is a bit nicer interface because you can still use brackets and the slicing indexing. Weave.inline is lower level, so you have more control, but you don't have all the nice features that you do in NumPy slicing index. So since this is being stuck into a C++ file, in C++ you can't overload the brackets and have comma separated things in there, so you have to use parents as a result. So that's why you're using parents instead of square brackets here. So it feels a little bit different.
So, but what's it in terms of the compilation? It's making the NumPy array into a callable.
There's a C++ class that you use an instance of a C++ class that's basically giving you all the functionality that you would want. And you can only index it into it. You can't use slicing indexing for Weave.inline. You have to use just bare indexing, but you can have comma separated indexing for multiple dimensional arrays. Yeah.
So earlier you said something about you wouldn't use Weave in a solution you were delivering to a customer. I didn't catch. Why is that?
Why is that? Just because Weave is doing a lot behind the scenes, kind of magically for you. And if you give it to a customer who doesn't have a compiler on or the right kind of compiler on their system, they'll just break and give this horrible error and they'll be like, what's going on? So if you have everything set up right, it'll just work like a dream. But it's not always the case that you have everything set up right, or if you don't have the right permissions to store those compiled modules because they're stuck in some default location, things like that. You can, there's nothing preventing you from doing that. I'm just saying that in my experience, I have
more brittle, basically.
It can be brittle, exactly, if you don't have control over the environment. Yeah.
So continuing with that thought, are changes to Weave well documented with respect to what version of GCC or whatever they need to use? Because I could see how that would be a nightmare on Mac or something.
Yeah, I don't know. I think it's using pretty standard features. It's not tying things out to very specific GCC or versions. I've never had an issue with that myself. Okay. I've never heard of issues with it myself either. So, yeah. Okay. Oops. Wrong direction. Okay, so that was Weave. Very, very briefly. I'm sorry I don't have more time to go into it, but I want to get to Cython. The Cython is kind of strangely, but now it's in terms of it's at least 10 years, no, close to 10 years old now, which I guess is old in terms of these things, but it's tried and true, very, it's battle tested, battle hardened, and got a lot of really nice features. So, who's heard of Cython before? Who's used Cython before? Okay, fantastic, good. So this will be relevant to a lot of you. If you've heard of Cython before, so you should be familiar. Cython is a Python-like language for writing extension modules. Okay? It allows you to mix Python with C or C++, and it significantly lowers the barrier to speeding up Python code. So remember that C file that I showed you with all the C code? Cython generates that for us, but we write code that feels very much like Python. Okay? There's a Cython command, and its only job is to create a C or C++ file that we saw, extension module. Then use some other infrastructure, disutil, some other compilation thing that knows how to compile C source files into Python extension modules to give you an extension module. The generated C and C++ code is heavily optimized in Cython. They took great pains to make it as fast as they can, while still being safe as safe as it can be for Python operations. And Cython, relevant to this specifically, to this entire conference, Cython has built-in support for working with NumPy arrays and Python buffers. And it makes numerical programming nearly as fast as if you were to implement this algorithm in C. And it's nearly as easy as programming Python in the first place. So there's a website. The kind of motivating example we're going to be using here is computing the Julia set. And I did not choose this because the guy from the Julia language is here for this conference. But this is from previous tutorial material I developed before, but it actually seemed pretty relevant to this course. So the core computation is very simple. You're in the complex plane, and for each location in the complex plane, you just iterate this function over and over and over again. The function is just z squared plus some constant value c. And the nth iterate of z is just iterating z by f of n, get the result back, and just keep on iterating. And what we see here plotted are the given some constant c. Each one of these plots is a different constant c, and some limit L. We are just plotting the escape time, basically the number of iterations before that the absolute value of z, the nth iterative of z, is larger than L. And for different values of c, you get these very intricate and fractal-like structures that result. So it's a very simple operation, and it's something that we can use to showcase how you can speed up Python code. And you actually get your hands on some coding and start working on some tutorial stuff here. So, and hopefully you can, if we didn't breeze through all the previous material too quickly, you can start to think about applying some of the stuff we've seen all up until this point. So here's a pure Python version of our Julia set computation. So this would be like a starting point. You just want to, you're trying an algorithm out, you just put it in a pure Python, you see if you get it right. So here we're passing in, this is the kernel. All of its whole job is just to iterate z according to this operation here many times until it exceeds limit. And we're passing in the z we want to iterate, the constant c that we're adding each time, and then the limit that we're testing for. And then we also have a cutoff here just to make sure this thing doesn't keep on going forever and ever and ever and never stops. So very simple. Count is initialized to 0. While the absolute value of z is less than limit and our counter is less than cutoff, you just do an iteration, add 1 to count, and this finally ends with just return count. So extremely simple core computation. Now our compute Julia function here is calling our Julia kernel internally. And what we're doing here is we're given our constant c, we're given n for the number of elements in each dimension, we're given a bound, that's how far to go in real and imaginary space, and our limit. Okay? So that's the interface of these functions. And these are the interfaces to all the other versions of this that we're going to see later on. Okay? We initialize our Julia grid that's going to hold our result. Our grid is just the domain that we're computing this over. And here's our C, our complex C value. We make sure it's a complex value. And now we're just looping over this in pure Python. Okay. And for every location in our Julia array, we are calling Julia kernel, and the result of that is now assigned to our Julia array. So very simple calculation. Nested for loop, so it's ideal for working on trying to speed this up with NumPy and Cython, things like that. Okay, so if you go into so terms of the exercises that we're working on now. If you open up the Julia shootout thing that you downloaded, should have been able to unzip it. If you're on Mac or Linux, just believe it's unzip, and the name of the file you downloaded. On Windows, I believe you should be able to use a double click on it and extract it to a directory. And inside of that directory, you will see so, unfortunately, I don't have time to, if there are setup problems, I'd love to make sure everyone's able to follow along and have everything set up and working, but unfortunately, there often isn't time to fix all the setup problems live. So, if you're unable to get things working, I'm happy to spend some time with you, during lunch break, things like that, to go through things. But you should be able to at least look at the source code. There's and follow along and understand what's going on. There's an exercise version of each one of these things and a solution version. Okay, so and if you open up that Julia shootout directory or thing that you downloaded, then you'll see a directory that looks like this with the contents in here. Let me move that top here so it's a bit further up. People able to get that opened up, downloaded, see nods. Okay, some nods. Raise your hand if you weren't able to download it or weren't able to open it. Okay, good. Everyone's able to open it at least and look at the source code. The main module is julia.py. So if you load on julia.py, you'll see this. It's 162 lines of code, so it's a bit long. But what's going on here is at line 31 or so are these imports. And each one of these imports is a different version of this Julia set computation. They're doing the exact same computation, just doing it in different ways. There's a pure Python version, which we just saw. And that's this here. You see there's a kernel, which we just saw on the slide. And then there's our compute Julia, which is what we also saw. Okay, so that's all that's in there. There's a Julia Cython solution, which we'll be compiling. There's a Julia Python NumPy solution. And then there's a Julia Multiprocessing solution. We'll be doing that later. And again, each one of these has the same algorithm implemented, just using different ways. So what I'm going to show you here is, well, first of all, in terms of the exercise, what you would do is you would open up, for instance, let's say you want to look at the Julia Python numpy.py. If you open up that file, which is the one we're on right now, what we're basically doing is we're taking the Julia set computation that we saw in pure Python, and we're going to implement it using NumPy array expressions and NumPy masks. Okay. For some of you, this will be completely brand new and very foreign, very strange. Okay, so I don't want anyone to feel like they have to spend too much time on something that doesn't make any sense or isn't relevant to where you are in terms of just learning NumPy and things like that. So for some of you, this will be a good exercise. This will be just at the right level for you. So you've seen NumPy before, you've seen masked arrays before, things like that. So I strongly encourage you to work on this example. For some of you, this will be really, really easy. So I definitely encourage you to work on this as well. Okay. So inside of Julia Python NumPy, there's our compute Julia function again, has the exact same interface that we saw. And it's heavily commented as far as what's going on in each line. Okay? And then if you look in this, this code here, there's a lot of setup at the top. So I don't need to be scrolling around so much. But all these lines at the top here are basically just setup. Okay? And then you'll hit this while loop, this while not all, np.all escape mask. Okay? And inside of that while loop is where you're going to be doing your exercise for this part of the exercise. And it's heavily commented in terms of what you're supposed to, what you're expected to do. And for instance, look for the to do tags inside of that file to see, and see exactly what you're supposed to be doing. So for instance, in this one, again, this is pulling out some parts of NumPy that unfortunately aren't contained completely inside of this talk. I wish it could be, but we just can't. So, yeah, I'm sorry, it's just impossible to cover all this material and get everything in. So that's why the solution file, the Julia Python NumPy solution, is provided for you. So you can step through that if you want and compare that to the implementation file to see what you're expected to do. Okay. So, for instance, inside of this, let me step through this with you just so you see what's going on. So, first two lines here, we're just telling NumPy ignore errors while we're going through this iteration because during this iteration, we're incrementing stuff a lot and we get some overflows. Okay. This specific algorithm, the parts where it overflows don't matter. And we've taken pains to make sure that's the case. So that's why we're turning off the errors so we don't get a lot of errors and warning output from NumPy. Okay. At the end of this function, the very bottom here, we're resetting the errors to be back on again. Okay, so we're turning them off just for this algorithm and then turning them back on afterwards. That's all that's going on there. All right, second part. Again, we're creating our Julia array, which is the output result of this computation. That's where the results are going to be stored. Then next line. We are basically creating two arrays that are our domain that we're computing over. For those who has seen ogrid before in NumPy, who has seen mgrid before, who has seen meshgrid from MATLAB or NumPy? Okay, they're all conceptually very similar. Ogrid is just like mgrid. And mgrid is very similar to meshgrid. What they do is they take, basically it's just allowing you to create an array such that all rows are the same volume. Let me put it on the board actually. So ogrid will give us two arrays back. We say minus 10, 10, 20J. It's got this bizarre syntax, okay? But what this is doing is it's saying start at minus 10, go up to 10, and give me 20 evenly spaced values between those bounds, okay? And give me one array that's minus 10 point So the first row is just going to be minus 10. The next row is going to be, like, I guess, what, minus 9.5, something close to that. So it's going to be two-dimensional arrays, basically. And then the last row is going to be 10. Okay, there's going to be basically something close to 0, if not exactly 0, in the middle here.
What's your second expression?
So this one is going to return two arrays, x and y. And this first one is going to be specifying, we want evenly spaced values just like this. The second array, this is going to be our x array.
I don't understand why it's two-dimensional.
Because...
So it's going from minus 10, the first row is all minus 10?
That's correct. First row is all minus 10s, and then we have...
yeah, that's a step, which makes sense.
There's 20 of these here, and then there are 20 of these here, right? The idea is you want the extents of these arrays to be the same.
Oh, I see what you're going to do.
And then the y array is going to be an array such that the first column is going to be minus 10, all the way down the first column. And then the last value in each column is going to be positive 10, it'll be 0, something like that in there. Okay. It's just a very compact way of creating these arrays, which allow you to basically have an x location and a y location for each spot in your grid. Okay. Which is what we need in order to compute our Julius set on this grid. Okay.
Sure. Sorry, I need to put my organizer cap on. At 10:30, the coffee is gone.
Coffee, oh great, thank
so
you.
Maybe you want to wrap up the presentation of the exercise and then people can start and get coffee at the same time.
Absolutely, yeah, that was my point. Thank you, yeah. So, good, I'll just mention that I'll set up the exercise and we'll break for coffee. And then we can kind of have a coffee break and some part of the exercise is kind of folded into the same part. Okay? So we'll have like an extended break / work on exercises.
How does it work when you have an imaginary step between?
Yeah, so that's some bizarre syntax. Unfortunately, it's very compact but not clear as far as what's going on. So thanks for asking. Let's just pull up Ogre's documentation, see if it's any better. No, it's not much better. So let me just write an equivalent version of this using linspace, so hopefully that'll be a bit clear. Who has seen linspace before? Either MATLAB or NumPy. Okay. So linspace, what it does is it takes, we're going to say x equals np.linspace, and we're going to say minus bound, n. Okay. And what that's going to do is it's going to give us this line here. Gives us a NumPy array with n elements, one-dimensional NumPy array with n elements. Excuse me. And the values in that array are going to start at negative bound, go up to positive bound. That's what the first two arguments are. And they're going to be evenly spaced. Okay. And it's going to include the last value by default. You can turn that on or off. You can say I want to include the last value or not. I think there's a keyword argument, endpoint equals true or false. By default, it's true. You can turn that off if you like to go from minus bound up to bound, but not including the last value, which is sometimes what you want. So here's x and y. Let's see here. X actually. We're just saying y equals x dot copy. And then what we're going to do is, well, first of all, let me ask you this. What's a very simple question. What's the dimensionality of x and y? Exact same arrays, exact same contents. What's the dimension? If I say x.shape, what will we return? N, right? So a tuple with a single slot n. Now, what I want to do is I want to use, let's see here, to get the equivalent of O-grid and M-grid and mesh grid and all that stuff. What I would do is so these are basically row arrays, right? I want to make one of them a column array so that when I combine them, I'm using NumPy's broadcasting operations implicitly. Okay? And the way I do that is by saying x equals, there are a few ways I can do it. The way I would prefer to do it, I guess, would be to say x.shape equals 1 comma n. Okay. So I just changed x shape so that it's now no longer just a row array. It's now it has. Excuse me. I'm sorry. I should have done the other way around. I went n rows with 1 column in each row. Okay. So now then, when I combine x and y, x is now n rows, 1 column in each row. Y is basically n elements in the rows. So when I combine them, I'm going to get this square grid that is exactly what I want. So if I add them together, it'll just be the addition of every location. If I index into them, it's going to do exactly what we want. So we'll see later on down here. Here we're creating an iterations array, which is going to be iterated inside of the while loop. And we're combining x and y. But we're first multiplying y by 1j so that it's now imaginary array. Okay. So iterations, what data type does iterations have after this operation takes place? That's right. Thank you. So, and it's going to be basically the complex number at each grid location, right? So that's exactly what we want. So iterations is going to be kind of the NumPy array that we're going to be performing our core iteration on instead of the while loop. So apologies for the O-grid confusion. Something I use just because it's more compact way of doing this stuff here. But this is definitely more clear as far as what's going on if you've seen linspace before. Okay, so we initialize our count variable to 0. Now here we're creating an escape mask array. And what this is it's just a NumPy array. We're saying zeros like, so it's initialized to zeros, and the like part means give me the same shape as this other array I'm passing in. And then we're saying we want the data type to be Boolean, so that's how we know it's a masked array. It's a Boolean data type. And we can use this mask array to mask off parts of an array and index into other parts. And the parts that we mask off aren't going to be changed when we update this array, things like that. So that's how you can control what parts of an array are updated and what parts are kept. Previous value will use masking. So we'll see down below exactly how to use masks. Here we're just adding some timing information by starting a timer. If you notice, if you look at the top, you'll see from time we imported this time function. Okay. All right. So for this exercise, I think the most instructive if I kind of walk you through it, just because it's the following exercises are a bit easier to follow along. So. So this first line here, so what we're doing first of all is this escape mask, what it holds, the reason we're creating this thing is this is a mask that is true for all locations that have escaped. So escaped, in other words, when we iterate through our Julia computation, whenever a value gets larger than our limit, then that value is considered to be escaped. It's escaped from our iteration, right? So we don't want to iterate that anymore. We're done iterating that one. So we want to make a note of that in our escape mask by setting that location equal to true to say, okay, this value is escaped now. We don't want to update that location anymore. It's 0 everywhere else because those locations haven't escaped yet. And we want to keep on iterating those because they need to be iterated more to see exactly what their iteration count is. Okay? So that's what the escape mask is holding. That's the information it's holding. It's 1 wherever a location has escaped. It's 0 where it hasn't yet escaped in our loop, and we still need to keep on iterating at that spot. So then our while loop, the conditional that we're testing each time through is whether everything has escaped yet. If everything's escaped, we're done. Because we know like the escape count for every location in our Julia set. If something hasn't yet escaped, we're not done yet. We need to keep on iterating through and find out what that spot's escape count is. So the first spot here, which I'll walk you through, is we're going to fill in the right-hand side of the new escape mask. And this doesn't necessarily make sense as we see the pieces below here, but the hint here is just kind of walking you through. It's composed of the logical conjunction of the locations that haven't escaped so far and locations and iterations that have exceeded lim. Okay? So, locations that haven't escaped so far is the inverse of escape mask. So not escape mask. And this won't, if you've seen mask operations in NumPy, this will make sense. If you haven't, don't worry about it. I encourage you to look it up on your own and look into NumPy mask arrays. But you can use Boolean and bitwise operations on NumPy arrays, and it works just like any other broadcasting operation. So, conjunction of locations that haven't escaped so far, and the locations and iterations that have exceeded lim. So, oops. Come on. Okay. So what this is doing is we only care about the spots that haven't escaped yet. Those are ones that are relevant to our iterations. We then combine that with those locations that have escaped this round. Okay.
Is there any reason you're using absolute value though?
Yes. So the data type of iterations is what, if you recall? Complex.
Yeah, perfect.
So lim is real value, so we need to, that's how we test to see if it's escape.
Perfect.
Okay, so we basically now want to update our Julia set, the result of this computation, with, so we've computed these new locations that have escaped this round. That's the new escape mask. Right? So at those locations only, we want to set to our count. So those are the values we want to update this round. Okay. So new escape mask is holding those values that have just escaped this iteration. And the value, their count value has been updated as well. So that's why we set only those locations equal to count. Now we want to update our escape mask to incorporate these new escape locations. So it's got all of these escape locations. So let's do that there. We're just doing the bitwise OR there, using array operations. We're updating our count to just incrementing each round. And then the last thing here is the core Julius set calculation. Okay, each time through our loop, we want to just iterating our whole array all at once, so that we're not, we're just using an entire array expression here. So who can tell me what the right-hand side of this should be? If we want to formally, basically this computation here inside of this while loop. So iterations holds our domain, right? And we have our constant complex value c that was passed in as an argument. So what do I type?
Just x squared plus c.
Yeah, exactly. That's right. So that's the core computation for this Julius set. Everything else is bookkeeping to figure out what's escaped this round, and if it has escaped, update our Julius set result with that, the iteration count at which it escaped. Okay. So that's it. That's the entirety of our NumPy version of the Julius set computation using masked arrays. Okay. Now, you may wonder, why in the world use masked arrays? Why can't I just use an if block inside of a for loop? Well, the whole idea here is performance. Okay. We've seen the Python version of this, which is a lot clearer, right? Hopefully it's a lot clearer. I find it much clearer. If you look at this version here, you see here's your kernel computation, and here's you're just looping through your array one by one, and then you're setting each value to the result of the kernel, right? Here's our Python and NumPy version. Okay, so everything we just walked through. That's what we're showing here. It's a lot more going on here. It's not nearly as clear as far as what's going on, but we'll see when we get to the timing section of this. This is almost 2 orders of magnitude faster than the pure Python version. So there is a significant performance increase. It's just not nearly as clear as far as what's going on. You have to do a lot more thinking to understand what's going on. So it's a trade-off. So we're going to break for coffee. Okay, some of the people who've already started to. It's fantastic. And I encourage you to look around, especially inside the julie.py file. You can go back and watch time during the break. Familiarize yourself with what's going on in that file. There's a number of things going on. I'll walk you through it, and then after the break, we'll start going through the Cython parts of the exercise, which are much closer to the Python version of the Julius set computation. So it'll be much clearer in terms of understanding what's going on. So, how long for the coffee break?
You can give all your data to the classification algorithm. Well, because
classification algorithm.
So can you announce a script just like a model?
Everyone will get started here. Everyone, your coffee break was able to crack open the julie.py file and start looking at it. Exercise a little bit. I'm gonna open it up here and just.
Are you starting again?
Yes, starting now. Are we good?
Oh yeah.
Okay. All right. Okay, so we saw this julie.py file briefly before, and at the top level here on line 31, we're importing our different versions of our, walking through our different ways of speeding up a simple Julia set computation. Pure Python version, we've seen the Julia Python NumPy version. Now we're going to start going into the Cython stuff. Okay. And I'll walk you through it, and then after that, we're going to see how to parallelize this operation with multiprocessing. And we'll see a exercise that is working with that a little bit. So the rest of this file then is just infrastructure for allowing you to run these different versions and compare their runtimes. And giving, so that there's a printer for giving you nice formatted output and stuff like that. There's a plot Julia function here that gives us those plots that we saw on the slides. And then there's a compare runtimes function here that's just going through our different versions, and each one of these sections here is just running a different version of that thing, of that version of the Julia set computation, and running it, getting the runtime, comparing it to the other stuff. We have a main function, which is our main entry point, and then at the bottom here, we have just some argument parsing to allow us to run this from the command line and tweak and determine whether we want to plot stuff or we want to compare runtimes for different things. There's a -n argument that allows us to control the resolution, how many grid points we're computing this on. So, as motivation, I'm just going to show you the runtime performance of these different versions. Okay. Hopefully this is, so what your appetite for, why we would want to pull out this infrastructure of, one, doing a NumPy like we've already seen, two, doing it in Cython, as we'll see this next step, or three, doing it with multiprocessing. So, if you're on Mac or Linux, and you're inside of this Julia directory, and you have everything set up correctly, so you have Cython, you have a GCC, a compiler available. What you can do, you should be able to just type make at the command line, and it's going to build all of our Cython stuff and everything that we need, and create an extension module for us. So all this output here is output from the compilation step for building an extension module from Cython. And all that's, if you look inside the make file, you see it's very simple. All it's doing is calling this one line. If you're on Windows, what you would do inside that directory, there's a build.dat file. You should be able to just run that from the directory. Did it work for those of you on Windows? Okay. Those of you who are not, I won't have time now to help you with it, but you can at least follow along, and I can hopefully have a little bit of time to sit down with you to try to get things working after the tutorial. I apologize for not having enough time to do all this, but setup can be a major issue if it's not working for some people, especially on Windows. So, anyway, if it runs and it completes successfully on Mac or Linux, you'll have a Julia Cython, you'll have these .so files that were generated. You'll also have some .c files that were generated. On Windows, you'll have the .c files, and you also have the .pyd extension modules, I believe. And those are the things that are imported and used by Python.
For the setup.py and make file, does that come with Cython, or you got to make your own?
You have to make your own, but if you look inside, so there are a number of things in here, but a lot of this is just boilerplate. So whenever you're have a Cython project and you're using just utils to compile it, you'll see these three lines. You'll see something like this where you're creating extensions. In here, you're just telling it the name of the extension. The source files, so here we have a PYX source file. And we're also wrapping the .c file as well. So we thought about that. And then we also give it extra compile args, which is an option here. Okay. And then you'll see the setup call. And those are like the main components for Cython. Import what you need, you create your extension, objects, and then you call setup with the right syntax. Okay. So it's all boilerplate, you just cut and paste from Cython's website, from the documentation, and you just adapt it to your particular needs. And so this what you've downloaded for this example can serve as a template if you like for adapting into your own project. All right, so we built everything. Now what we can do is we can say Python julia.py, and just by default, what it's going to do is it's going to plot our Julia set. Resolution larger than my screen can handle, but there we go. Well, larger resolution, you would see all 4 blocks, but you see here, these are just Julia sets for different constant complex values C. Okay, I hope some of you have been able to get this plot to come up when you run Python julia.py. One thing you can do is you can change the resolution. You can say -n, and by default, I think it's 100. So you get 100 by 100, 100 grids. Let's say, I don't know, 800 instead. It runs, and you see now we get a much higher resolution version of the Julia set. I don't know, maybe it's not as clear on the display there, but you saw my screen is clearly higher resolution result. So that's by default, that's what the Julia.py script is giving us. What we can also do is instead of just plotting, we want to compare the runtimes, we can say -a compare, and we're going to kick the resolution down here. Let's say 200. So what this is doing is it's running all versions of our Julia set computation that we imported. So PurePython, NumPy, Cython, and Multiprocessing. And it's comparing all their runtimes and giving us output. So if we scroll up here, see here it's telling us the Python only version, is the kind of benchmark we're comparing to. It took 2 seconds to run, and if we use NumPy expressions, we get about an order of magnitude speed up for this size of array. We use Python, so we're using, well, I don't want to go into too much detail on the rest of these steps yet. I'm going to get ahead of myself. But the point here is that when we start pulling in Cython in varying degrees of, just different degrees, you get more and more speed ups. So here's one version of Cython where we're just speeding up the kernel computation. We get an order of magnitude speed up. Then those are multiprocessing stuff, we'll go into that later. Here's all Cython with no specific optimizations, and we bump up to 130 times the speed up. And here's Cython with NumPy specific optimizations, and we're almost at 600 times the speed of our just pure Python code. So pulling in Cython to different extents gives us, a lot of payoff for our efforts. And so this is kind of the background, keeping back of your head, okay, if I'm using Cython and I use it correctly, I can expect often for numerical, iterative, lots of looping algorithms, orders of magnitude speed up. I don't make any promises, but you can, this is very common to see these sorts of speed up for algorithms that are, especially algorithms that are CPU bound. All right, so now that's motivation. Now we're going to get into Cython. So
Just one quick question before you.
Yeah.
So Cython works with the multiprocessing library, so you can write your Cython code and have it batched across your cores.
You can, yeah. So the result of Cython, of course, is just an extension module, which you can import that extension module, use it just like any other thing from Python, and then you can call that from within multiprocessing and it works fine. As long as your nodes can access that module, they can import it and use that Cython compiled code, or that compiled code.
But your modules, your Cython code doesn't use numpy. How could you use numpy with multiprocessing?
Repeat the question, sorry. I didn't
Can
hear
you
you.
use numpy with the multiprocessing module too?
Yes, you can. We'll see in the slide deck examples of doing that.
Okay.
And then, yeah, it's certainly possible.
It's new rate isn't long. It's on long.
Yeah, so it's your responsibility to take care of blocking and data integrity and things like that, and make sure you aren't reading and writing from the same location without, safety. But yeah, it still works. It's not multiprocessing. It's not like multiprocessing knows about NumPy and knows how to work with that intrinsically. But multiprocessing does have though features for the name's escaping me right now in terms of what the names of these things are. But if you look at the multiprocessing documentation, you can create objects, container objects that are safe, that are locked when they're accessed and unlocked when they're read. Okay. Oh, go ahead.
Sorry, just one quick question. How did you generate the timing table you just displayed? The command line?
If you look inside the julia.py file, it's all there.
Thanks.
Another dumb question. I get an import error with Julia's Cython solution.pyx.
Okay.
Is there some .py file that's supposed to be going on with that?
I'll need to take a look and see, but it'll have to come after. Maybe we'll be stopping here a little bit to give people time to work on stuff, and I'll stop by and I'll look at compilation issues. So that's my fault. I apologize. What's going on is, so in this file, what's going on is it's calling the kernel, right? But it's calling it before it's been defined. So one thing you can do is just move this kernel function up above. So we can take that and put it up here, like so.
Could you define a function prototype in C, or is that not what
Sorry, say that again.
Could you define a function prototype like in C?
You can forward declare stuff if you want. You could just say, or you can also, there are other ways to do this. I don't want to go into details. Yeah, there are other ways. The easiest way is just to put this function definition, the kernel function definitions at the top, right after the Cython functions comment. So I apologize for that. I should have tested this out a little bit more. I'm still feeling a little very count reference before. Did you recompile? I did too. Yeah, you're right. Count needs to be initialized to 0. Yeah, you're right. Sorry. The other error that I made, I'm sorry, is that count needs to be initialized to 0 inside of kernel. Okay, before the loop. Now you're going to be typing count, but you also need to make sure you initialize it to 0. Now if you recompile, things run. So let me write on the board here the line you use to test everything out. This is a little verbose. Okay, so this is the line you use for running everything and comparing the runtimes on Mac or Linux. Actually, probably we'll do the same thing on Windows. Perhaps you need a different path for Python, Python.exe or something like that. Just need to make sure you're you're running your Python that you want to use, and running the julia.py script, and -a compares the action that you want to take. So that's comparing all these different versions. And then -n200 is the number of grid points you're using. You can bump that up or take it down if you like. That allows you then to compare the runtimes of your version. Yeah.
For this C NumPy part, right now it says cdef, CNP array, and then it has all the type of Julia. And then the next line says Julia np.empty. It should be one line, right?
Let me see here. So what function is that again?
It's in compute Julia opt.
Right. Okay. So we'll go into this part of in the next part. I should have sectioned that off. Sorry.
Okay.
The ones you should focus on right now are just the kernel function. So this one here, I'm sending a kernel. Type everything there, and then you also want to focus on compute Julia no opt. You're typing stuff there. That's done for you. And then compute Julia opt is the next part. So we'll wait to do that. Okay, so I wish I could spend more time and allow you to have more time on these exercises. Fortunately, we're moving through this rather quickly. I hope this is instructive to see. You can take Python code and you're adding type information to it to speed it up with Cython. Now, in this compute Julia Cython function, we've typed all our arguments. We have typed the local variables I and j, x and y. Here we're just creating a NumPy array. Julia, grid are just both straight NumPy arrays, and that works perfectly fine. We don't have to type them. We can if we like. We'll do that in the next section. Here we're typing, well, the reason this line is highlighted is because just to point out that since both I and n are both typed variables, this Python for loop is converted into a C for loop underneath the covers for us. Same thing for this, with this for loop here. And this line here is a C-level function call. So it's fast, it's not wrapping stuff into Python objects, unwrapping them, and doing the boxing and unboxing that usually occurs. Now, one thing, if you this is essentially our function here. There's still a good amount of yellow in these lines. The for loops are just straight C loops, so they're pretty tight. But these lines here there's a lot of stuff going on. And remember, grid is just a NumPy array. Here's our we create our grid. Here's all the code that results. All that messy stuff is what's going on. Here's our core line here when we call kernel. If you look deep down inside here, you'll see the call to kernel. Let's see if I can find it. Here it is. So that thing there, this ugly mangled sucker, is that's our wrapped kernel function inside of Cython. Okay, that's just a pure C call. But all this extra stuff around it is to get this assignment over, this indexing and assignment into our NumPy array. It's doing very general Python style stuff, right? So for instance, in Python, you can index with a negative value to an array, right? You sure as I can't do that in C. So if you give a negative index into this thing, Cython has to put all these checks around it to make sure that it converts it to the right positive value integer, and then indexes into that thing in C. Likewise, so it's like wrapping around, or you could use a slice in here if you wanted to. Cython has to figure out all this C conversion to get that slice operation to work. There's a lot going on there, right? So one thing we'd love to be able to do is have those parts of the file set up. And you can do that when you pull in Cython's NumPy support. So we'll move through this pretty quickly. But I encourage you offline, if you want to, do the same operation, pull open the Julia Cython.pyx file, and inside of there, there's a NumPy version of our compute Julia function, and you'll be adding in this information, this typing information there. Here we're typing our NumPy arrays, and the way you do that in Cython is with this somewhat funny syntax, but at the top here we're saying we're actually saying import NumPy, saying C import NumPy as CNP. So Cython has a C import statement that exists alongside the Python import statement, and that's for importing stuff specifically from Cython. Thank you. And that C import allows us to access things from the C level. Okay? You can think of it as it's analogous to Cython. It's analogous to pulling in a header file in C. But you just use a C import syntax, and you'll see that in the source file. We'll open it up. And here we're typing this thing as an ND array. We're telling it the underlying data type, the number of dimensions, and the mode, basically whether this is C contiguous or Fortran contiguous. We're giving this information to Cython so that it can generate much faster code as a result. The only difference between this version here and this version here is that we've added in the body these typing lines, and then we've also added these decorators at the top. And what these do is it turns off the bounds checking. So we're saying we don't want Cython to generate code to check to make sure we're not out of bounds in our indexing. We don't want to take the speed hit for that. We're also turning off wraparound checking. So we're saying basically we're guaranteeing this function that we're never going to use a negative index into these arrays. So Cython doesn't have to generate code to check for that. So we're going to get faster loops as a result. So now our core stuff stays the same. We just added more information. Yeah, go ahead.
Sorry, so it doesn't actually get overwritten when you do Julia equals np.empty. It's just, it knows that previous column.
Yes, you're right. Julia is now just think of it as a typed array. So it's just like, it's exactly analogous to if you said I, so you say, you see the unsigned in I, and then you say I equals 0, it's not overwriting I anymore. It's putting 0 into that C memory location, right? It's analogous to that. There's a lot more going on, but it's analogous to that.
Pardon, with the bounds checking and getting, I can't use a negative index and get Python behavior.
That's correct. Right, so if You're saying if bounds checking is on,
If bounds checking is on.
it will handle general Python indexing. Yep. If it's off and you use a negative index, then if you're lucky, you'll get a crash. If not, you'll get something horrible. So, yeah, go ahead.
So the business with the negative index, it only matters if you inadvertently run off the end of it. Is that right? Or you can use it, or you can't use it, period.
If you turn off bounds checking, or sorry, if you turn off wraparound, so bounds checking is, in Python, if you index into an array, Numpy array or a list or something like that, you index outside bounds, you'll get an error, like an exception, right? Cython, if you don't put this decorator here, then Cython will also give you an exception. Like you'll get an exception in here, like just same Python behavior. If you go in there and turn it off and you index outside of the bounds, it's just like you index outside of bounds in C. You're basically dropping down to more C-like behavior here. So Cython lets you go down to more C.
But you can still use negative indexes, provided you yourself take responsibility for not letting things go over bounds.
Right, if you only turn off bounds checking, but you keep wraparound true, then you are allowed to use negative indexing. Yeah, they're separate things. That makes sense. Good question. So the point here then is, so kind of the general point is we've started with our general Python version, and we just incrementally added typing information. Here we're adding, our first version of typing information to the kernel. Now we're adding typing information to the compute Julia function. Now we're going in there and we're adding more information about Numpy arrays. And this is all documented on Cython's website, so I encourage you for more details to go there to read up on this. These are the kind of the essential bits and pieces that you need to type Numpy arrays. And you get a speed up at each version, at each level of speed up, at each level of effort. So here's just a summary of our speed ups that we're getting that I ran a while ago. These is for n by n of 200 by 200, so pretty small arrays. And we're, our Python plus Numpy is about an order of magnitude speed up. Python plus Cython's kernel is, less than order of magnitude and less than Numpy, curiously. So what this version is doing is it's all Python except for the kernel. We're just pulling that in from the Cython source file. So that's the only part that's been sped up. This version here is all Cython without any Numpy specific stuff, and we get 150x. Cython with Numpy optimizations gives us 670x. And this version down here we didn't cover, but this is wrapping externally. So we wrote the same version in C with OpenMP, so we can access our cores. And we get a 1300 speed up. Okay. So the point here isn't necessarily that Cython's really fast. Actually, the point is more that Python's really slow for numerical stuff. Okay? For doing these nested loops, Python's really, really slow. And there's a lot of room for improvement. If I turned off OpenMP and just showed you the C version without accessing, parallel cores, this would be 670. Take my word for it. It's the same speed as Cython with Numpy optimization.
What about multiprocessing?
So that is, I have it here. No, I don't. We're going to be going into that next. So this is just on a larger array, just to compare for larger sizes. And you see the Numpy version and the Cythonized kernel are basically the same performance. Okay, so I'm behind the gun on time here, so so the slides are here for you to use, to look at and peruse. There's a slide deck on multiprocessing that we'll be covering briefly. There's also a slide deck on MPI for Pi, which we will not be covering. That was, remember, an optional installation, and I didn't want to put anyone through the pain of installing that when it doesn't work. It's horrible. Multiprocessing is part of Python, and it allows us to access parallelism from within Python. Now, some of you may have heard of, well, so Python does have a threading module and allows you to have threads within Python. But who here has heard of the GIL? Okay, none of you have heard of it. I won't go into it very much, but it's just, I just bring it up to mention that it means that the threading module will not give you any net speed up on your code. What it does gives you is concurrency and processing, and I guess stuff that won't lock up. So if you have GUI, you can spawn stuff up on a thread and your GUI won't lock up. That's why you would use threading. But it won't give you any speed up for your code. So that's essentially what the limitation that the GIL is imposing on us. The way you get around that is by using multiprocessing. And it provides access to task-based parallel computing using separate Python processes. So it's when you run several processes in multiprocessing, it's actually creating a new heavyweight OS process, another Python process that's running your code separately. And it's in its own address space, so you have to worry about communication between these two. They don't share memory. By default, you can set that up so they do, but by default they don't. So there's a bit more work you have to do to get multiprocessing working, but it does allow you to access, however many cores you have on your machine or a cluster or things like that. So it's part of the Python standard library, so it's there for you by default. You don't have to worry about installing it separately, things like that. It's cross-platform. It'll work on different, Yep.
If you want to compile a large huge amount of data in parallel, doing the parallel processing as in MATLAB, can we do in Python also?
You can. MATLAB has a number of things that are nice for just kind of automatically turning on parallelism for you. That's not quite to the same level yet in Python, but there are projects that are working on that. And you can use multiprocessing to do things like that.
Do you have an example of multiprocessing
for processing large amounts of data in parallel? Unfortunately, we don't have time today, and I wish I did have more on this. When I normally teach this, you give this module half a day, and we have more time to go into things like that.
How can I get that code or something?
I can sit down with you and point you to some sources online and things like that. So.
Multiprocessing is one process per core.
So it's just going, you can, if you want, you can, we'll see here in a little bit, you can create as many processes as you want. It's obviously makes sense to use as many or fewer processes than cores. You're not going to get any speed up. If you have 10 cores and use 1,000 processes, they're all going to be competing for the same resources, right? But it's not tied to your system at all. It's not going to limit you to that.
With hyper-threading, you do 2 processes per core.
Yeah. If your underlying infrastructure allows for more, then you can speed up from that. Yeah. So what's in there is low-level stuff. We won't be covering that in much detail at all. We will be looking at task pools, though. They're a higher-level construct, and they're very nice to use. They have automatic scheduling, shared memory, and you can have shared memory object wrappers, and it has support for functional iterator like design support, things like that. The module is useful for batch computing, for embarrassingly parallel computations. I've used it a lot in my graduate work when I had a lot of just batch style jobs to churn through, and I have it, coded up in one version serial, and then I just hand it off to multiprocessing, and it just gives me, if I have 8 cores, then I get up to, you never get all the way up to 8x speed up, but 4, 5, 6x speed up, and so it's often a very, very easy way to access to scale up an algorithm on your local machine. If you're doing parallel computing with minimal shared state, this works out really well. You can do GUI programming and do calculations in the background process of multiprocessing, and many, many others. So it's all documented online. That's just talking about multiprocessing versus threading. The core of multiprocessing is the process class. We won't be going into this in great detail, but this is just to show you that you can create a new process, and then you can say process dot start. And here's just a very, very simple example. We have a worker function that we're going to be calling in separate processes. And here we're actually creating our processes. We're actually creating 2 of them. And we give it a target argument. That's the thing we're actually going to be calling. And the arguments that are going to be passed to that worker when it's called in a separate process. And then we just say p.start for each one of those processes. And those are run in separate processes. And then we call p.join on each one of those processes so that the parent process will wait for those child processes to finish before it exits. There's facilities for communicating between processes while they're running using queues and pipes. Here we're just showing an example of getting something from a queue inside of our worker. The main process, when it's run, it's creating a process, passing in a queue as an argument, and then starting the process that's running remotely. We're putting something on the queue in our main process, in our parent process, and you see that the child process waiting on that queue.get line, and then it gets that result, gets the parent string from the queue after it's sent over the wire to the child process. So, apologize for going this quickly for time constraints, but this is just to show you that you can have inter-process communication using queues inside of multiprocessing. But everything's going to be serialized, sent over the wire, so over some communication layer, whether it be IPC, things like that. And then, so it's not for free. It's not like these processes are sharing state or anything like that. So if you have a huge NumPy array that you're sending over using a queue, you can do it. But if it's a lot of data, it's going to take a lot of time in communication. So you want to make sure that your workers, the processes that you're spawning are doing enough work to justify the communication overhead that you're using during these computations. So this is all still low-level stuff. Okay. There's also pipes, which are 2-ended queues. You can send and receive on both ends of a pipe. So you can basically have the parent sending on this end and the child receiving on the other end. And the child sending on this end and the parent receiving on this end, so they can basically there's direction to the messages on these pipes. They're handy to have as well in your toolkit. You can synchronize processes using locks. And I don't want to belabor these points too much, and this is pretty low level stuff, but if you need to guard a resource so that only one process accesses it at a time, you can use a lock to make sure that happens. You just acquire it, access the resource, whether it's an output stream or some object, some file on disk or something like that. And then when you're done using it, you do lock.release to release the lock. And that will guarantee that only one process accesses that resource at a time. Synchronization. The thing I really want to get to are task pools, because they're the most useful. And they're the thing we'll see in the example. So there's this pool class in multiprocessing that allows us to create task pools. And what they are is, think of it just as a pool of workers, so a group of workers, a group of worker processes that sit there waiting for work to be done. And what they do is, once work is dispatched to them, they go off, they take that function, whatever callable, and arguments that need to be called and run in their process. They run it, get the results, and give it back to the calling process, and then go in and get the next chunk of work to be done. So they're constantly just doing work, coming back, and asking for the next chunk of work to be done. So it's giving you basically load balancing and this ability to access all your cores for very, very little work. So here's an example of using a pool and using the map function with a pool. If you remember, we saw the map function previously. It's a way of applying a function to an iterable. So it's another way of like writing a for loop. One benefit of map is that you can use it with multiprocessing and get parallelism in a for loop for free. So if you can convert a for loop to a map, then you can hand that map to multiprocessing and get that done in parallel. So here is an example of okay, so there's a very, very simple prime computation. This does not guarantee to it's using formats, prime primality test, which doesn't capture every prime, but it's probabilistic, I think, to a certain degree. So you can, the details are not important. The only important thing here is just that this is our worker. Okay? We're going to be handing a number p, and we want to know if that number is false or it would return false and the number p if it's not prime, and true in p if it is prime to some degree of certainty. And that certainty is controlled by the number of iterations you use, and that's controlled by k. So that's our worker. We're going to be running that in parallel. And here's a main function here. Okay, so first we're creating a multiprocessing pool. Then we are calling pool.map, and we're passing in the format prime function. That's our worker function, and then we're giving it an iterable of things to iterate over. And it's what map is going to do is going to break up that iterable into chunks, send that chunk with that function to a process. That process applies that function to each one of those things, gets the results, wraps them up, sends them back, and then we get the result of that in p to nums. It's all being done in parallel, and then in our main process here, we can then iterate through p to nums and see if things are prime or not. So let's run that. This is just simply, showing the results here, and showing how it works. This plot here is indicating the scaling of this algorithm as we change the number of processors in our pool. 1 is down here, 2 scales as we'd expect, so it's 3, 4 is starting to deviate a bit, 5, 6, 7, 8, 9. This is an 8-core machine. So we still get a speed up, but it's not, it starts diverging from a linear speed up like we would hope after 4 or so. So the maximum speed up is about 4.5. And once we get to 9, we're getting a net, we're starting to drop off because we're using more processes than nodes. So they're all competing for the same resources. So this is indicating to some degree, 1, that multiprocessing does have overhead. 2, that, well, in this particular case, there's a good amount of overhead communication overhead compared with the actual calculation that's going on. So if you have more work being done per worker as compared to the amount of communication that's required, you will get better scaling as a result. And that's just a general feature of multiprocessing. You want to keep your communication down as much as you can and bump up the work done per node so that you're not spending all this time and just swapping stuff around to allow your computations to happen.
What if you raise your chunk size?
One more time.
What if you raise your chunk size?
Yeah, you can tweak as well. Yeah, you can to see what sort of performance you have. I've not tried that on this, but it'd be interesting to see. So, very briefly, You can use multiprocessing with NumPy. People don't often do this, but you can. You can basically break up your NumPy arrays into different processes, and you're able to use the shared C types from multiprocessing to allow you to grab the underlying buffers and things like that. I can't go into much detail here on it. Unfortunately, it's an interesting topic, but the performance is not that great. You'll get generally much better performance, I find, if you have your workers just work with local NumPy arrays as much as possible. And you don't try to do too much NumPy stuff with multiprocessing directly. Here we're creating a shared C types array, this raw array object in multiprocessing, but again, the performance is not that great. You can get better performance out of it. Like I prefer to use something like a Cythonized worker function and use multiprocessing on top of that and just simply pass our NumPy arrays around without using this raw array thing. It's in this example slide here.
What about a memory map array? Would that be a better way to share?
So that is a way of sharing. Yeah, that's right. And its performance is also problematic, but it's sometimes the only way you can do processing on huge arrays, right? If you can fit an array in memory, you want to be able to access it in parallel with multiple processes. You can use NumPy memory mapped arrays to get that to work. So I only mentioned that remote.
What does that output indicate? I don't understand.
So our worker function here is fill array, and it just takes the little piece of the array that is passed in and it fills it with the value I. So we're creating two processes, and we're passing in views of the array to those different processes, different views. And we're filling, we're having it fill the first one with 1 and the second one with 2. You see the resulting array R now has, the first part filled with 1, the second part filled with 2. So it's just showing you that the two processes, separate processes, fill their part of the array with different numbers, and then the resulting array R reflects that. So this is just showing, the typical way I've seen multiprocessing used is for batch computations. For numerical computations, typically you pull out a more specific solution. Libraries such as PyNPI, NPI4Py, IONCL, there are all these solutions here that you would consider using for very heavy numerical stuff. So, very unfortunately, I'm up against the clock here. So, noon, right, is the end time. All right. So, I apologize profusely for not getting to iCloud. There are just 2 slides on it. I was just going to show you the most basic usage possible. And so there's nothing more that you can't learn on your own, but this is always a good motivation just for trying out something new in tutorials. So I'm going to steal 1 minute and go through PyCloud. And just for those of you who are interested in that sort of thing. So there's all sorts of